Okay, we are starting to record. And I'll share the screen again. Excellent. Okay, and yes, the question about how to form priors for novel experiments with no historical data. How do we form our priors? Do we use pilot data? Yeah, well, I'll just keep talking about priors for a little bit, and maybe some of that will answer that question. And then if it doesn't answer your question, we can revisit. Okay, so yes, first of all, people say, well, priors are too strong of an assumption. But yes, that's true. You have to make assumptions, but prior distribution is not the only assumption that's made when you're fitting a statistical model. It says, well, we'll just use frequentist because it only uses a likelihood, but likelihood part of it also has assumptions. Like, let's say you have a general linear model, whether that's Bayesian or not, you have to assume that the relationship between X and Y is linear, follows a straight line, and that it has normally distributed error around that line. Well, that's not really, that's only a approximation of what is going on in the real world. That's only an assumption, right? Normal distribution is a mathematical equation that people came up with because it's closely approximates things that happen in the real world, but at best it's a rough approximation. So like you're assuming that that is close enough to model what's going on, but that's still only an assumption. And so basically it's not a good argument to say you can't make assumptions because all statistical models are based on assumptions. So it's just like, which assumptions are you making, you know? And another argument I would say in favor of priors is that you can kind of get around the philosophical objection to priors by saying, well, usually in practice, the data sets we use are large enough that the prior distribution doesn't have that much influence on the results. It's really the likelihood that is driving the bus and having most of the influence on the results. Well, then why use priors in the first place? Because they help constrain your estimates to a more reasonable range, and that makes the computations of actually fitting the statistical model a little bit easier. So it's more of a practical tool than actually something that we're really, thinking that hard about exactly what the priors should be. We're just constraining it so it's not an incredibly big negative or incredibly big positive number. Like, we're keeping the results within an order of magnitude. And that actually, when we're using these computational algorithms to fit models, it makes the computations easier. And actually, in many cases, for a lot of type of mixed models, the likelihood-based methods, the algorithms cannot converge. They can't even get an answer. They'll get stuck. And so we actually have to use priors. We have to use the Bayesian approach to even give us an answer in the first place. So that's, I think, a very strong argument, a practical argument in favor of this approach. And lastly, the third argument is, yes, of course, the results are sensitive to the priors we assume and any assumption we make, but that's fine because no matter what, we should be checking the sensitivity of any results or predictions we make to our assumptions, and priors are not, right? If you are making an assumption, you should examine that assumption and check if your results are sensitive to that. So one way to do that would be to use different priors, for example, and see if the results are sensitive. And if they don't change as a result of changing the prior, then that's good, but you should say so in your publication or presentation, and that will help people trust your results to show it's not just a function of what priors you put. But if they do change as a result of the prior, you should also present that, and that's just evidence that can be put out there and let the reader decide what they think of it. What's not a right thing to do is if you would know that the results are sensitive to your choice of prior or to any other assumption you make, it's not really great to present results from a single model with a single set of assumptions and a single prior as if that's the only true right result, because that's a little bit dishonest. So definitely, if you do find it sensitive, you should present that. So first, I'm going to give one example without doing code. I'm just going to give an example, just explain it to you, and then the next example with prior distribution, we'll actually go in and look at the code, at the model results ourselves. So let's take a look at, we're going to imagine there's a prior, and we're going to imagine there's some data, and how is the posterior distribution, our final estimate of the answer, influenced by that. So let's say we have developed a avian vaccine of some kind, and we want to know if it can help grant immunity to some disease. And we already have, we know that the baseline rate of immunity of unvaccinated birds is already 50%. And we can have a prior assumption. We'll say, well, we're going to make a very conservative assumption and say the vaccine is most likely to have no effect. Like, this is just some new, new compound we're testing out. We have no prior belief that it's going to have a strong effect, but we'll allow for that possibility. We'll say the most likely prior outcome is it has no effect, but we'll assume that it can also have a beneficial effect or even a negative effect. So let's show, what does that look like? Well, first I'll say, well, here are some different scenarios of data we collected. Let's say there are 3 different experiments, and we vaccinated animals, and then we challenged them with a virus to see if they were immune to the disease. Well, in one scenario, let's say we just had enough budget to test 10 animals that were vaccinated. We found 7 were immune and 3 were not. So we observed 70% immunity rate, right? In scenario 2, we tested 50 animals. We got 35 immune. We still had a 70% immunity rate. In scenario 3, we got 70 out of 100, right? So every time in these 3 scenarios, we saw that 70% was what we observed in the data. Now, if you were just using likelihood, your maximum likelihood estimate is 70%. There's no way it could not be, right? Because that's what you got in the data. Yes, the more data you get, the narrower and narrower the confidence interval around 70% is going to be, but the estimate is still 70% if you only use likelihood and no prior, no matter what, because all you can use in likelihood is the data that's in front of you, right? Well, here's, let's say we had a prior. Now here I'm using the same prior every time. This orange line is the prior distribution. So like I said, we thought the vaccine is most likely to have no effect. So the highest prior density is at 50%, which is the same as the baseline rate. And we said, well, it could be above it and it could be below it. And the likelihood is what we calculated off of the data. And you can see the likelihood always has its highest density at 70%, because that's what we observed in the data. Whether we observe 10, 50, or 100 animals, every time it's peaked at 70%. But you see how narrower here with only 10 animals, the likelihood is very wide. Like if you could easily get 7 out of 10 if the true probability was like 90%, or maybe it was 40%. You could still get 7 out of 10 by random chance. But if the true probability was 70%, you're very unlikely to get 90 out of 100 or 40 out of 100, right? Because that's not as likely if the true probability was 70%. That's why it's narrower. The likelihood is narrower at the higher sample size. Well, see, the posterior is just taking these 2 distributions, the orange line and the blue line, and multiplying them by each other. So you see that with only 10 animals, our posterior has moved. Our most likely belief is not 50% anymore. It's like 60, but it's not exactly 70. It's somewhere in between. And that's with 10 animals. Let's say we had 50 sample size. Well, the posterior is even closer to the likelihood. It's still not quite exactly the same as it, but it's a lot closer. Our prediction would be like centered around 65%. By the time you get to 100 animals, the posterior is very close to the likelihood, and our prior influence is becoming less and less. The more data you get, the more our likelihood, which is based on the data, is informing our answer, and the less impact the prior has. Right? So as our sample size grows and grows, this prior would basically have no impact anymore, and the posterior would look just like the likelihood, because our data the information in the data is so much more than our information about the prior belief that it is kind of taken over. Any questions on that? Yes, so my take-home message from here is your posterior is informed by the prior and the likelihood, and the more data you have, the less important is your prior belief, and the more important is the data, which it should be, right? We want as scientists, we learn from the data, and so we want to learn more the more data we get. And our prior belief becomes less, it goes back in the rearview mirror, the more data we get. Yes, and so that's just a verbal summary of that the influence of the prior weakens and the likelihood gets stronger the more data you get, because that's evidence basically. So okay, so that's kind of, I'm going to move away from pure lecturing now, and for the rest of the time, it's all going to be hands-on. We're going to actually look at the code as we go, okay? So this is the first thing we're going to do is do an example of the prior distribution influence. Like in the example we just did, right? We had different likelihood every time, so we had different data, but we had the same prior every time. Now what I'm going to do is the opposite. I'm going to have the same data every time, but different priors. So now we can look at how important is the prior for determining our answer, our posterior. Like, and as I hopefully showed you, if you have a lot of data, you really don't have to worry as much about what priors you choose, because it doesn't have a strong influence. Like even our n equals 100 was already like big data, basically, in terms of it took away the influence of the prior. But what if you have a very small data set with only a few data points? Then the prior is going to be influential. So I'm going to do an example on, I guess, a somewhat controversial topic where there might be strong prior beliefs and people might think differently about stuff. So we're going to, this is a good time for us to go, and I'll now show you the Posit Cloud setup, and I'll start my workspace, because that's what we're going to be doing for the rest of the time. So hopefully everybody was able to use their invitation link that I sent out in the email to create a workspace on a project within the workspace on Posit Cloud. So I'm gonna go into that. Oh, I see there's a question in the chat. Yes, how would you determine minimum or ideal sample size when planning out an experiment? Well, the way that actually the Bayesian approach you can do that by you can simulate from your prior distribution, and then basically by simulating data, assuming different parameters, you could then say, well, let's say I have n equals 10. This is the answer I'd get. Is that a good enough answer for you? It might not be, because it might still be too uncertain. So you can, yeah, I usually I would say a simulation approach is best for doing that kind of power analysis. Yeah, you can do statistical power analysis in Bayesian just the way you can with classical statistics. That's kind of a vague answer. That really deserves a better answer, but I'm happy to follow up with more detail on that. So let's see. So I'm gonna go switch over to the. Okay, so here's the Posit Cloud workshop workspace. So hopefully when you went in here, you'll have this November 2024 Bayes workshop. And then once you're in that, there's a new project. So I see many people have already started one, which is great. If you didn't yet, you go in here and click on New RStudio Project. And you can name it, but you don't really need to. So the first time you start it, it will take a few seconds to load up, but it should go much quicker if you ever quit out of it and start again. Okay, so hopefully when everybody fired up their Posit Cloud, they should see the same thing that I do, which is here's the RStudio. Basically, this is an RStudio, essentially R running on a remote server. But this version of R has all the packages installed that we are going to need for the next 2 days. And it has the worksheets. So we're going to open this lesson 2 worksheet. So just click on that lesson 2 worksheet. And then it'll pop up in here and we'll be able to run. And you can see there's, once you get down to the real model code, there's some blank spaces we're going to have to fill in. So, and also another nice thing about this is the model fits are already saved here because the Bayesian models that are run by Stan, whenever you run them, they have to compile the model basically in C++ code. And the first time you run it, it takes a minute to compile. And so to save time, I've had them all pre-run so that if you're doing this, instead of having to wait for the model to sample, it's just going to sample immediately because I didn't really want to get into issues of that today. We're talking more about the stats today. So this should help us do that by saving time. Yes, so the first thing you need to do, if people are not familiar with R is kind of run line by line. So this is a script. This document that I just opened is a script, a text file containing R code. And we run the code in this console. You can type individual commands in there and run them, or you can run them from a script. So
sorry, what was that?
Yes, we can if you want to run individual commands, you could put 1 + 1 in here and hit enter. It will give you the answer. We can also use this script to run code that we've already typed in. And so I'm going to go ahead and run all this setup code. If you highlight any code, and then you can either click run up here, or you can hit Control Enter. It will run. So what this code is doing is loading all the packages, the external collections of functions that we're going to need to run our code today, and it's going to set some plotting options as well. So I'm going to run that. I hit Control Enter, and it will run. Different messages will pop up that you can ignore. Okay, so back to the slides. I'm going to switch back and forth between these things. And yes, so we've set plotting options, and if you're running this on your own local machine, it'll create a directory to save the fitted model objects in, but that already exists on our on this server. Okay, and the next option we have to set is the model fitting options for the brms package. And basically what this is doing is it's saying only refit the model if the code changed in between last time it was run. but since if we shouldn't have the code change, it will load the pre-cached object. And if you were not able to get command stan R to install on your own machine, if you're doing this not on the POSIT cloud, then you can run this without the back end set to cmd stan R. But don't worry about that if you're on the remote server. So I'm just going to run this line 31 here. I'm not going to run this. And you can, if you have your cursor on a line, you can just hit Control Enter or click on Run to just run that line without highlighting it. So I'm going to put my cursor on this line and hit Control Enter. So far, so good. If we want to take notes on the R script, will we be able to download it afterwards? Yes, you can. You can do that. Yes, so whenever you edit this and save it, then you could select it and go to More, and then you can export that, and you can download it to your local hard drive. Yes, great question. Mahesh, I see if you have a technical issue, can you please go to the breakout room, to the Zoom room, and Grant will be able to help you. Thanks. Right, so yeah, that brings me to another point. This demo server is for demo purposes only. I'm only allowed to use it if we pinky promise to not upload any government data. This is an unsecured server, right? It's not a government secured IT. This is only for demo purposes. So all we're going to use on here is example data, no government data, right? So don't upload any data to this. If you want to run this stuff on your own data, you have to use your own machine. All this software is also on Skynet as well. So you could do it on Skynet too. And I'm happy to help you with that. But this is only for demo purposes. So thanks for your cooperation. Oh, not to mention, I only have limited space on my account on here. So this, I may delete after this workshop is over. I'll probably at some point delete all these workspaces. So they're not guaranteed to stay around forever. Yes, so let's go back to the slides. And so we're going to talk about impacts of genetically modified organisms on non-target species, which is obviously, GMOs are kind of controversial and people have strong beliefs about them one way or the other. So I thought it's a good example about priors. And all the example data that we're going to be using today is from this really nice package called AgriDat. It's an R package that has a bunch of, it's basically all agronomic or, ag science data sets with example statistical models that go with them. So, so if you have that package installed, you have all these example data sets available. So that's what we're going to use. And there's one data set in there called Gathman BT, and that is a very simple, very small data set. It just has the abundant, so, people say, well, if we have transgenic maize with BT, the toxins that are in there are going to have impact on non-target species that are not the pest species we're trying to reduce, right? And so, but some people say, well, actually, even if it does have impacts on non-target species, it might be safer than conventional insecticide because we're not spraying insecticide everywhere, so you could go either way with it, right? And so this study looked at some non-target arthropod species that's a good species, we don't want to kill it, and measured how many of them there were on some GMO corn and on control isogenic, not GMO corn, right? It's very simple data set. It's just a mean of two groups. So if you go in your console and you type in R, if you type question mark followed by the name of an object, it will give you the help documentation for that object. So I'll just show, you don't have to do this, but I'll just show you. If I put question mark Gathman BT, it'll give you documentation of what publication it came from and stuff like that. It just has 16 observations, 8 8 BT corn and 8 control. That's all it's got. Very small data set. And the abundance of 2 different arthropod groups on those 16 samples. And this is the first code we're going to run. We're going to use this data function, which is basically loading example data from one of our libraries. And then let's make a box plot using ggplot of the 2 means, or the 2 distributions of the data. So I left some blanks there. You can see what we're going to do. Well, in ggplot, you have to tell it what variable, what column in the data is going to be the X, is going to be GEN for genotype, and Thysanoptera, I guess, is the name of the arthropod taxa that we want to know about. And then we're going to say geom_box_plot, which means make it into a box plot. So I'll type that in. You follow along with me. X equals genotype, GEN, and Y equals Thysan. And we want geom_box_plot. So first, I'm going to run this line to pull up the data. So now you can see that in our environment, we have our data, Gathman BT. And then I'm going to put my cursor on line 39 and hit Control Enter to run it. And there's the box plot. So, okay, we only have 8 data points in each, but it's like, okay, here we go. We got 8. Here, the mean abundance is higher, looks like, or the median at least, is a lot higher on the BT corn. Great, right? So, so that's just a look at the data. Now, what will we do next? Well, we have to, I thought it would make more sense to change it so that the intercept or the reference level is the control group. So we're going to do that. And that means if we get a positive parameter estimate, that means the BT corn has higher abundance of the non-target species in the control. And so GMOs are good or whatever, that's what it would mean, positive there. And then we're not gonna do a Bayesian analysis yet. We're just gonna do a t-test, right? This is the simplest kind of statistical model we can do. We can say, do we have enough evidence to reject the null hypothesis that those 2 groups of data come from the same population with the same mean? Is there enough evidence of that? Only considering the data. It's only using the likelihood. We do not have any prior knowledge or beliefs in that. That's what a t-test does. So first we have to re-level, which means change the factor levels so that the REF reference level is the ISO, which is the control group, isogenic line. So we're going to hit Control Enter to run that line. And then on this next line, I've left some blanks in there. We're going to do a t-test, which is the function t.test. And it's done as a formula. The formula for the t-test is our response variable, Thysan. And then we use the tilde genotype. So it says, is there a difference in Thysan by genotype? And then we say, what data do those 2 variable columns come from? Now we'll hit Control Enter and see. What do we get? Let me make this bigger. We can see it gives us a t statistic, a p-value is less than 0.05. So by the standard cutoff, we say there is a significant difference in the means. One mean is in the control group is about 8.7, the other is 14.2. And there's a confidence interval around that difference. So far, so good? Okay, so that's our frequentist analysis. We've said, okay, based on just this sample of 16 ears of corn or whatever it is, there is enough evidence to reject the null hypothesis that these have the same abundance. Well, let's now do the Bayesian version of that t-test, which uses priors. Now we see that in the data, you can see there's like about some go up to 18 and down to 4. The response variable varies between 4 and 18. So we could say then a difference in two group means of 5 would be pretty big, because it's like, you know, the entire range of the whole data set is 14. So anything that would change the mean by 5, I would say, is a big effect in that context. What I'm going to do is I'm going to fit this same model 7 different times. Every time use a different prior. The first, by default in BRMS, if you don't specify a prior on the fixed effect, it will give you a completely uninformative, a completely flat prior with equal prior probability for any effect size. Now, some people would say, well, that's good because we're not putting any subjective beliefs in there, but that's actually an unrealistic thing to use for most situations, because we usually at least know the order of magnitude of the expected effect size, even if we don't know if it's going to be a positive effect or a negative effect. If we know that we usually, you know, only observe abundances between, you know, 4 and 20 or whatever it is, we're not going to get 100 as our mean difference, right? That's not even possible. So we at least know the order of magnitude of it. So we should at least use our priors to constrain it to a reasonable range of values. But by default, it does not do that. It just gives you a completely flat prior. So how are we going to fit the flat prior? Well, oh yeah, sorry, before I do that, these are the other priors that we're going to use. They're always going to be normal distributions every time. You see these 6 ones are all normal distributions, but with different mean and standard deviation. Some of the priors have a mean of 0. That means we think the most likely, right, the normal distribution has a peak at its mean, right? So that's the most likely prior belief that there's no difference between the two means. We say the most likely thing is that there's no effect. But if it has a standard deviation of 5, that means it's pretty wide normal distribution. We think that there's a decent probability of an effect in either direction, but it's exactly centered on 0. We don't have any belief of whether there's more likely to be positive effect of BT or negative. We could also do a normal with a mean of 0 and a standard deviation of just 1. So it's a much narrower. It's still centered on 0. We still say it's 50-50 whether it's positive or negative, but we say it's probably a very small effect. There's very low probability of a large difference, positive or negative. We think that's very improbable. We could also change up the mean of the normal distribution to not be centered on 0. We could say a mean of 5 and standard deviation of 5. So that means we think that BT has a positive effect on the abundance of this bug, but we don't know. We're very uncertain. We have a high, we're leaving a lot of probability on either side of that. We could also have a 5 mean standard deviation of 1. We're really very sure that it's a strong positive effect of BT. And I'm also going to show you the opposite, where we have -5 as the mean and both wide and narrow standard deviation. So we say, well, in one case, we think it has a negative effect, but we're not sure. And this one is like, well, we're very sure that it has a negative effect. So those are the 6 different priors. We're going to try them all out. And yes, sorry to switch back and forth so much. I did not change up any of the sampling options. I'm using defaults every time. Basically, when the sampler runs, it runs different Markov chains to sample the posterior distribution for different numbers of iterations. But since we're using such a simple model, the default number of iterations is more than enough, because we're just sampling a very simple model. It's just a t-test. It basically only has one parameter. So there's no need to like change that up. And so, but every time you see that the the model formula every time is Thyssen by genotype, the same as it was for the t-test, and the data set is the same. I put a random seed in there so that you would get the exact same answer. The random sampling is starting at the same point every time. And I've also saved this in a pre-saved object. And see that by default, I did not specify any prior distribution, so it's just going to use the flat prior. And you can see here, these are the 6 priors we just talked about. Normal 0, 5, normal 0, 1. And this class equals B means the fixed effect beta, fixed effect in the model. They call it B in brms language. Since usually in statistical notation, beta is what you call a fixed effect, so it's B. So yeah, all this is the same, except the only thing that changed between this one, model 2 and model 3, is just the numbers inside of the normal distribution in parentheses. That's all we're changing. Same model, same likelihood every time, but different priors. So we'll start, BRM is the function that we use, Bayesian regression model. And the formula is Thyssen by genotype. That's going to be the same every time. And the data is always the same. Gathman.bt is the name of the data frame that it comes from. So we'll run that. And since the model is already saved in our workspace, it will just immediately run. Now, if you were on the Posit Cloud server and you type something wrong, it will start to compile and run the model because it will say that something changed since you last ran this model. So that's a good check that you're doing it right. I see that we have, yes, command stand path has not been set yet. I did set this so it should, when you start the Posit Cloud server up, it will automatically set the command stand path to tell tell R where to find the stand software. I think if you restart the R, if you go up here and restart your session, if for some reason, then it should set that path again at that point. Or you can follow what Grant put in the chat. You can set the command stand path using that command. Okay, so that's the flat prior. I'm not going to look at the results of it yet. I'm just going to, let's just run everything, and then we'll compare them all at the end. So the second model, we're going to use the argument prior, which sets the prior distribution. And it's going to say prior parentheses. The prior function is used to define prior distributions. And then we say, what is the statistical distribution? It's normal with a mean of 0 and a standard deviation of 5. And what parameter are we putting that prior distribution on? We're putting it on all parameters with class equals B, all fixed effects. There's only one fixed effect in the model, so it's just going to put a prior on that one parameter. That's model 2 with a wide prior centered at 0. We hit Control Enter. And that ran also. Again, I'll compare these all at the end. Now we're going to do a very strict prior, again, centered at 0. This is model 3, normal with mean 0, standard deviation 1. Then hit Control Enter to run that. And then it says, okay, well, now we think BT is more likely to have a positive impact, but we are uncertain. That's a mean of 5 and a standard deviation of 5. Run that. Now we're going to do our 5, 1, because we really are very certain that it has a positive impact in this scenario. In this one, we think it's more likely to have a negative impact. We'll put -5 as our mean and 5 as our standard deviation because we're uncertain. Run that, Control Enter. And then lastly, -5, 1. We are very certain that it has a strongly negative impact. So we've run all that. And if anybody, yeah, so I left at least for most of them, just the two numbers blank. Again, if you don't get this all filled in, that's okay, because you can just look at my output as well. And so the next commands, you don't really worry about these. These are basically some code. This is just to show you what's going on. We want to pull out the posterior estimates with their 95 lower and upper credible interval bounds. Those are the quantiles of the posterior distribution. And that'll tell us our estimates of difference between the means. Because when we do Monte Carlo sampling, we get a whole vector of values, which is the posterior distribution of the parameter. We can calculate the median of that long vector of values and the quantiles. And that's what we call the credible interval. It shows the uncertainty of the posterior distribution. And we're going to use the 95% interval, although you could use other numbers. So I'm just going to highlight that whole code. I didn't leave any blanks there because this will pull out the posterior estimates. Now we want to.
Hey, you are not in the meeting? The statistics meeting?
Okay.
Quentin did?
Can you please mute yourself? Thank you. And now we're going to plot it. Now I wanted to just I'll show you the object we created is called Gathman post estimates. If you look in the data, we have a median, a lower 95, and an upper 95 column, and each prior distribution has a name. And so we're going to make a GG plot of that. We're going to put prior on the x-axis, the different prior distributions. We want the median of the posterior estimate to be our point estimate that we're going to put on the y-axis. Lower 95 is the minimum on the error bar that we're going to show. And upper 95 is the upper endpoint of the error bar. And we're going to use this geom point range, which means to put a point with an error bar on it as our plotting graphic type, basically. Geom point range. So this is kind of the interesting part here. So once we hit enter, we can see, control enter, we can see these are our estimates of the difference between the means, the posterior estimates, taking into account the data and our prior beliefs. Every time the data was the same. We have the same likelihood every time. We just have different priors. Now, this estimate is the flat prior. We had no prior belief at all. And it gives an estimate of about 6, which is the same as you would get from the t-test. And you can see the 95% credible interval is pretty wide, but it all is sort of positive. So there's that means there's a 95% posterior probability that the true value of the difference is between the two ends of that error bar. So we think there's evidence that BT has higher abundance. And now if you look at the normal prior with a mean of 0, standard deviation of 5, you get a very similar result to the flat prior. It's about the same, because that's basically, we said there's just a pretty high prior probability of positive and negative effects. It didn't pull it one way or the other. But look at what the normal with mean of 0 and standard deviation of 1 did, right? We say, well, we're saying there's 50-50 of positive or negative, but we said there's very unlikely to be strong effect in either direction. So the data, since we only had 16 data points, was not enough to move our prior belief that much, right? Like, this is still a mean of very close to 0. And so actually in that case, the prior had a strong effect. What if we thought it had a positive effect, but we were uncertain about it? You can see that's the normal of mean with 5, standard deviation of 5. That also looks about the same as as having no prior at all, because as it turns out from the data basically confirmed our belief, because the data showed about the same difference of 5 that we thought there would be in the first place. So our prior was similar to what the data said, so that's why it didn't change. But if we set a normal with mean of 5 and standard deviation of 1, you see it has a mean of near 5 or 6, but the credible interval, the uncertainty around our estimate is much narrower, because we already were so sure beforehand of even getting the data that it would have a positive impact, that the data just helped us confirm that, and we're even more sure than we were before. And these ones I think are the most interesting. Let's say we had a prior with a mean of -5 way down here, but a standard deviation of 5. Because we were so agnostic or so uncertain about our prior beliefs, with a mean of -5 and standard deviation of 5, we actually have basically a very similar result than having no prior at all, because it's just a very wide prior. But if we already started with mean of -5 and standard deviation of 1, if we were very sure before getting the data that BT would have a negative effect, you can see we actually get the opposite posterior estimate of all the other ones are positive, but this one actually is -3 or so. So we actually have a totally different posterior inference if we had a very strong prior belief that GMO would have a negative effect on the arthropod abundance. So I think that's actually quite interesting. So we see, this is kind of the most extreme example I could get for you, because it only has a very small data set with n equals 16. And this shows kind of the most prior influence you could get. And so this is, again, and I picked a very, very artificially narrow prior. So this means if you have very strong prior beliefs and not very much data, you're going to get your result back similar to what your prior beliefs were. But even if you don't have very much data and your prior beliefs are uncertain, then it will then the data will kind of be the biggest determining factor in what your posterior is. Again, if anybody needs help with the technical getting the code to run, please go into the Zoom room. The link is pinned at the top of the chat, and Grant will help you. And so, yes, so this is basically the priors that had the most influence on the conclusions was based off of the standard deviation of the prior more so than the mean. It was how wide is that prior, how tight is it, is what's really influencing your conclusions. That's putting, basically in the Bayesian approach, the information doesn't just come from the data, some information comes from the prior. So the tighter the prior is, the more information you're giving it in addition to the data. And so it has more influence on the answer that you get. Does anyone have any questions on that so far? Yes, I see there's some questions. Is it better to start with a flat prior if you don't have any previous data? Yes, I would say so. And in those cases, I would just use, again, a prior that is going to constrain your estimate to appropriate order of magnitude. Like you could use, a normal prior with a mean of 0 and a large standard deviation of, like, if you expect differences on the scale of 0 and 10, you could put a mean of 0 and standard deviation of 10, and that will make the computations work better, but it won't have a strong influence on your conclusion. And is a normal prior appropriate for count data? That's a good question. So we're talking about the fixed effect, right? Like the difference in the mean of two groups, right? Like a treatment might make the mean go up and it might make it go down. So that parameter could be either positive or negative. And so you could use a normal prior on the fixed effect, even if it was count data, it doesn't matter, because normal is kind of one of the only distributions that can be positive or negative. You could use a normal or a t distribution because they have support on positive and negative values. So you have to have a prior distribution that includes positive and negative values if you want to be open to the possibility of a positive or a negative effect. So yes, And if you have previous data, could you use the mean and standard deviation from another experiment? Yes, you could. And that is actually a very common situation. Right. Again, we don't do our science experiments and studies in a vacuum. We have usually, even if it's not exactly the same study, a similar study system. And, you can at least, yes, the standard deviation at least could be used to determine the order of magnitude that you expect to see, and that could be used for your prior. So yes, James, you definitely could. And so the last thing I'm going to do in this example, and after that, I think we'll take a short break, is there are also, we covered this last year, you probably don't remember, you can calculate something similar to a p-value. It's not exactly the same as a p-value in a Bayesian analysis, and we call it a maximum a posteriori value. And that means our posterior distribution has a median, a point estimate, and we have a null. It's sort of like a null hypothesis test. Our null value would be a difference of 0 between the two groups. So what we do to get this p-value thing is take our posterior distribution and say, what is the probability posterior of the null value versus the probability of the point estimate that we observed. If that ratio is very low, close to 0, that means we have very little posterior evidence for the null being probable and very high posterior evidence for what we observed. So like it's going to go close to 0, similar to how a p-value approaches 0, the more evidence you have to reject the null hypothesis. And there's a function in this package called Bayes test R called p_mat, p_mat, that if you feed it a prior distribution or a posterior distribution, it will calculate that value for you. And so I've just stuck that all into a function that will make a table of p-values for each of these priors. And so I'm gonna hit, I didn't leave any blanks there, just hit Control Enter, Gathman _ p-values. If we type that into our console, it will print it up. Gathman _ p-values. And here we have each of our 7 priors. What is the p_mat value? You can see that it kind of corresponds to this graph over here, right? These are pretty low, close to 0, showing there's decent evidence that the difference is bigger than 0. For this normal 0, 1, the p_mat value is very high, meaning we have no evidence, basically very little evidence that this is different from 0. And the interesting one, this p_mat value for the -5, 1 is very, very low, and in the other direction, right? So we have our evidence that it is different from 0 in the opposite direction here. Again, that's just sometimes I do present these values in a manuscript as another way of characterizing the evidence, because while it's not exactly the same as a classical p-value, it kind of presents it in terms that people that like p-values and null hypothesis tests are familiar with. But it's the ratio of evidence for the observed difference or the ratio of the evidence for the null versus the evidence for the observed difference. The lower, the stronger the evidence. Any questions? Why don't we take a break and come back at 10:30 Eastern, 9:30 Central. I'm going to go use the restroom real quick, but I'll be back to answer any questions after that. And I'll just go ahead and mute this mic until we get back. But feel free to ask a question in a chat. All right, actually, before I go, I see another question in the chat. Would you present multiple p-values in a publication? Say one with a flat and one with a data-driven prior. That's a great question. Yes, I think, as I mentioned before, it is good to do a sensitivity analysis of your priors. If I would go that far, I would probably, you could probably present, anytime you do stats, right, you're making assumptions. You kind of have to pick some and defend them and present those as your main results. And then you could kind of have a supplemental, for example, showing that that the results are not sensitive to your choice of prior by showing the results with different priors. Like, for example, like you say, flat and data-driven prior. Well, yes, the prior should not be driven by the data that you collect in this study. It's sort of double dipping if you would look at the data that you're about to analyze, then make a prior, because that's using information from the data. The prior is not supposed to have any information from the data. But yes, previous data you could. Can we derive a tentative prior based on maximum and minimum values? Yes, 100%. And that's kind of what I did in this case. Yes, I didn't really look at the data per se, but if you looked at the range of values that in reality, you would know kind of what is an expected range of values you'd see, and then you can use that to inform your prior. Yep. Thanks for the questions. Again, I'll be right back. Hey, Bob, I don't know if you there right now. I see you just had a question of how to describe that test in a manuscript. Yeah, for this example, I didn't provide example of how to write it up in a manuscript, but I did for some of the later for all the later examples I do. So we'll go through that then, and hopefully that will help you see that. But yes, you couldn't, this isn't really a t-test, so you couldn't call it a t-test. The Bayesian model is not a t-test. It's only called t-test in classical statistics because it's basically using a t distribution to get a test statistic, but we don't have a test statistic that we're comparing to a null distribution in this case. So we wouldn't call it a t-test. We would just say that we would have to say that it was basically a regression of abundance on genotype. Yeah. But yes, for the rest of today, every time we do anything, I'll show you how you'd write it up in the methods and results of a manuscript. But yeah, when I do show those p-map values, I usually cite the paper that they were first presented in, because not that many people know what the p-map values are yet. So there's a paper you can cite for that. Yes, and so somebody, Zach said they tried using a t distributed prior instead of the normal prior, and yeah, so that should give a very similar result. Yeah, because well, a t distribution is very similar to a normal with fatter tails. So if the standard deviation is wide enough, the tails are kind of fat anyway. So yeah, it shouldn't make a big difference. But some people do like to use t distributed priors instead of normal because fatter tails means they stick out longer and have more probability of extreme values. So some people say, well, it's more conservative to use a t distribution because you're kind of saying, well, I'm pretty sure that the effect isn't going to be big, but I'm leaving a little room of doubt that there might be an extreme effect in either direction. And yes, normal goes out as well, but t also has a little bit higher probability of extreme values. So that's why instead of using normal of 0,5, they might use t distribution with 0,5 and like a low number of degrees of freedom, which will have fat tails. Great. So if everybody, well, I'll give it one more minute to make sure everyone comes back, and then we'll start up again. Oh, I see Bob has another question, that some tests need a power test to confirm that the data has enough samples to be robust. Is there something that is needed for Bayesian statistics too, something like a power test? Yes. Yeah, I mean, obviously, Bayesian is just there's nothing magic about it, right? I mean, you still need the more data, the better, and you want to have enough data to be confident in the inference that you make. So yes, there isn't statistical power for false negatives and false positives isn't quite the same in Bayesian world because we don't have a yes or no cutoff. We sort of have a more continuous measure of evidence, but you still have power. So, the Bayesian approach is usually, unfortunately, with like classic things like t-test and ANOVA, you have those formulas you can just plug and chug and get your power number out. But with the Bayesian, you kind of have to do a more simulation-based approach to do your power. Yes, and I'm happy to help anyone with that. If you're trying to do Bayesian stats and want to do a power analysis, I can help you. But there's some literature about it as well, which I can pass on. But yeah, it is. Yeah, I mean, it sounds complex. Yes, I mean, the sort of downside of some of this stuff is it's a little bit harder, and Bayesian, well, while Bayesian statistics is actually older than frequentist statistics. It hasn't really been done commonly for very long because it needs a lot of computational power to get answers. So a lot of these kind of common techniques that have been developed over the years for frequentist stats are not there yet for Bayesian. So you have to kind of do more of your own thing, which is kind of hard. So that's kind of one of the main barriers to people doing this more. But yes, I appreciate the discussion. So I'm going to get started again with the content here. Yes, I had one more slide about this prior thing before we actually go into the generalized linear model part of the day. And I just wanted to say something about the priors one more time. Basically, what I just said before and mentioned again is it's kind of the width of the distribution, how narrow it is. That means how strong our beliefs are, shows how influential the prior is. So like normal of mean of 0 and standard deviation of 1, yes, we're saying it's 50-50 if it's positive or negative, but we're assigning such low probability to extreme effects to large effects that's actually very informative. You're actually it's not really objective. It's actually still like a strong belief, even though you're not saying it's going to be positive or negative, you're saying it's not going to be a big effect. Now, I also don't want to say that just because the Bayesian result that doesn't agree with frequentist maximum likelihood result is wrong, right? Like, well, here's the flat prior that's basically the same as what the t-test would say. These ones are very similar to that. This one's not, so this one must be wrong. No, that's not what I'm saying. Like maybe this is right. That just because the prior influenced the result doesn't mean it's wrong. It could be right. Like we only had 16 samples. Like, do you really want to base everything you think about GMOs off of 16 samples? I mean, not really, right? So it's actually could be okay and even good to have this very conservative prior. That means we need a very strong influence of the data to pull our belief off of this conservative, it's not going to be an extreme difference situation. That actually could be good. So that was kind of the point that I wanted to make there, that skeptical prior could actually be better. And this is an extreme example because I think most data sets we use are not going to be quite so small. I mean, some are, but I don't think it's great to draw big conclusions from a tiny data set anyway, and this just kind of illustrates that. And ultimately, if you really are concerned about the influence of the prior, you should document it and let the reader decide, let that speak for itself without saying one is right and one is wrong. So I just wanted to make that point before we proceeded. Okay, so now for the fun part. That was basically, we spent, half an hour talking and then an hour doing basically variations on a t-test, which is cool, but like, do you really need the Bayesian approach for that? Not really. I mean, the classical approach does just fine. So what we're going to talk about for the rest of today and tomorrow is some real statistics where the Bayesian approach can shine. It can actually get you answers when other approaches fail. And that is in the world of generalized linear mixed models. So what are those? Let's talk about them. Yes, so we're kind of getting out of the territory of simple models and going into some slightly more complex statistical models. But nothing that is out of the realm of what people do every day in ag science. This is still the type of models that we need for what we do. We're not being needlessly complex. We're being as complex as we have to be to fit our data. Okay, so this may be review and it may be new to you, but either way, I'm going to go through it. Now, this is not Bayesian or not Bayesian. This is what we're talking about now is true for all statistics, whether it's classical or Bayesian. So this is part of the reason I wanted to talk about this stuff today. Is this is important for you to know, even if you don't do Bayesian stats, you might want to just learn about generalized linear mixed models anyway. So this could be useful for you, even if you're not convinced about the whole Bayesian thing. So let's talk about general linear mixed models. We're not going to generalize the world yet. We have, this is the form of the model. We have a response variable y, and we're saying it is a function of fixed effects, which is, we got data x, those are our fixed, our predictor variables that we care about, and then we have b, our fixed effect parameters, plus z times u, which are basically, z is like a matrix telling us which block every observation belongs to, and u are the random effects. So it means our y, the normal, has a mean and a standard deviation. Our mean is a function of fixed plus random effects, a combination of fixed and random effects added together. That's a mixed model. Mixed because it has a mixture of fixed and random effects. And it has, this sigma is like the residuals of the model. It's just the noise around it is normally distributed. Some error is positive and some error is negative. It's exactly symmetrical, normally distributed error. And we also say the random effects have a normal distribution. They're called random effects because they are random variables drawn from a distribution, which we always say has a mean of 0 and a standard deviation. It's mean of 0 because some blocks have a slightly higher mean and some blocks have a lower mean, but they're all centered around 0. I use block because people are familiar with the agronomic studies, and it doesn't have to be a block. It could be, you know, a hospital. If you have a study where you're testing a drug at many different hospitals, some hospitals have a higher, you know, success rate than others for other reasons besides what we're trying to study in here. But we will call it block because y'all do, you know, field studies in ag science. Yes, and so as I said, the random effects and the residuals of the model are all normally distributed. Some are a little higher than that, or a little lower. I don't know which. It's random. And the same goes for the random effects and the residuals. What are the ranges of u and sigma? Well, sigma is a standard deviation, so it has to be a positive number. The standard deviation is always positive. You can't have a negative standard deviation. But u, the random effects, can be positive or negative, right? Because it's a normal distribution with a mean at 0 and a standard deviation that's positive. So it has half of its mass is positive and half's negative. So some random effects are positive and others are negative. Okay, that's great. Why can't we use this idea for all our data? Well, because not all the data will fit neatly into that box and be modeled with a normally distributed error. You can't force, I mean, right, it's all an approximation, but in some cases that approximation is not good at all. In many cases it's great, like if you're measuring weight of animals that's centered around a mean, and some are a little higher and some are a little lower, normal is perfect for that. But what if your response variable is binary and has only 0 and 1 values? Then you know, like if you're measuring whether an individual got a disease or not, or whatever. Well, it's you can't get a normally distributed error centered at 0 with about half of them positive and half of them negative in that case. You're not going to get that. Or what if you're measuring the concentration of an element? A lot of times concentrations are very skewed distributions. You have a lot of low values near 0 and a long tail of high positive values, but you can't have a same long tail going in the other direction because you can't have negative concentrations. Concentrations have to be 0 or greater. So it's going to be asymmetrical. It's going to be skewed. So your residuals are not going to be normally distributed, centered at 0, half of them positive and half of them negative. They're going to be some really high positive ones. It's not going to be normal. You can't assume normal distribution. You're going to get biased answers if you do. So, and also, if you try to use that model to make predictions, if you fit model assuming normal errors and but it doesn't make sense for that data, you're going to get predictions that also don't make sense. Like if you have binary data, if you observe, okay, I have a treatment and a control group. Let's look at how many in the treatment group got the disease and how many in the control group got the disease. What you're modeling is the probability of getting the disease. Is it different between the two groups? If you assume normal errors, you might get predicted probabilities that are greater than 100% probability, or you might get a negative probability, a less than 0 probability. Those don't make sense at all. And if you fit a normal model to a skewed data, like to concentration, you might get predictions of a negative concentration. Again, that doesn't make sense. You can't have a negative concentration. Now, some people might not care because they don't care about prediction. They only care about inference, like are the means significantly different or not. But even if you don't care about that, it's still a problem if your model makes bad predictions, because for a model to make good predictions, it has to be a good fit to the data. If it's making predictions that aren't even present in the data set and not even possible, it's not going to be a good fit to the data. You need to make sure your model fits the data to make valid inference. So you have to, that's why we need to have predictions that make sense. Any questions on that? Cool. So what did old school scientists do when they got some data that wasn't normal and wanted to, or didn't have normal residuals and wanted to analyze it? Well, they just transformed the data. Sometimes they would just take a whole list of transformations and just like throw, I say this as if it is in the past tense, but people are still doing this every day. They just like take their data and try out a lot of transformations until one works-ish and like makes it look kind of normal. That in some cases that can still be an acceptable way to do it, especially log transformation. I still like it because it can turn additive relationships into multiplicative relationships, which is fine. But for the most part, transformation introduces bias, and we shouldn't do it if we can avoid it. What we want, I mean, and hopefully everyone should want this, we should find a model that fits our data instead of torturing the data to make it fit this one very specific model with normal residuals. Like we want, why should we, the data, the model is not real. The model only lives in a fake world of statistics. The data is the only real thing. So like we don't want to like take the data even further from reality to make it fit this model that's not even real. We want to keep the data as it is and find a model that fits it as well as we can. So that's why generalized linear models are such a useful tool, because they are much more flexible and can fit a lot of different types of data that your normal general linear model can't handle. So how do we do this? Now, this should look very similar to what we showed a couple slides ago, except instead of normal, I say, well, it could be another distribution besides normal. It can't be, there's still some limits on it, but I won't get into that today. It could be any of a wide variety of distributions, and they all have their own parameters. We're just going to call those parameters theta. They might have more than one parameter. And so still, we have our fixed and random effects here. But instead of saying it's normally distributed, it's now can have any distribution. And now instead of y being on the left-hand side, we have g, a function g of y. Well, what is that? Well, it is a link function. That is the relationship between the predicted variable and the distribution function. Because, right, x times b plus z times u, you can, if you add and multiply numbers together, it could be positive, it could be negative, it could be anything, right? Like it's adding and multiplying numbers together, you could get any number you want out of that, right? It's positive or negative, doesn't matter. But our normal distribution works good with that, because normal distribution can also be positive, negative, it can be anything you want. But some of these other distributions can't. Like the binomial distribution can only be 0 or 1. So we have to use a link function to convert this variable that can be any number you want into the scale of the statistical distribution, which can only be in a certain range. Make sense? That took me a long time to like actually comprehend. I did not really understand that for like the first few years of doing this stuff. So yeah, it's a hard concept. Oh yeah, and another point is the norm. We still are going to stick with normal for the random effects. Pretty much all GLMMs, even if this distribution is some crazy thing, are still going to use normally distributed random effects. Yes, some really like next level people get away from that, but I'm sticking with normal for the random effects. And that's what pretty much everyone does, because for random effects, we're still going to say some are a little higher, some are a little lower. We don't know. So like normal is good for that because it's centered around 0 and symmetrical. So we're sticking with normal for the random effects. That's all very abstract. So let's go and actually do an example with a data set about seed germination. And we're just going to do, this is not a mixed model yet. I'm not going to throw random effects into this yet. It's just going to be a generalized linear model. No random effects. So it's not GLMM, it's just GLN, generalized linear model. And why is it called generalized? Well, again, going back to mixed again, generalized means it allows response distributions that are not normal. So it's more general class of distributions. Linear means it's a linear combination of effects. Linear means multiplying and adding things together is linear. So like this is a linear combination because it's just multiplying and adding things. So that's why it's linear. It doesn't mean straight line. It means multiplying and adding things. That's what linear means. And mixed is a mixture of fixed and random effects, but we're not going to do the mixed part yet, just generalized and linear. It's just a fixed effect right now. So again, I'm going to go and use another example data set from this AgriDat package. It's kind of a cool example. There's a plant called Orobanche aegyptiaca that is a parasitic plant. It does not have chlorophyll. It gets all its energy by leaching energy from the roots of a host plant. It just sort of like digs into the roots and pulls out sugar, and that's how it grows. It doesn't have photosynthesis. But that means it needs a host to survive. So if it starts to germinate and there's no host nearby, it will die. So the seeds can detect chemicals that the host plant is giving out in the soil, and that's what stimulates it to germinate. It's kind of neat. So I don't know why someone was doing this experiment, but they have a 2x2 experiment factorial with 2 factors, genotype. So there's 2 different genotypes of this plant and 2 different extracts. So they took extracts from bean plants and cucumber plants and treated the seeds with them to see which one would stimulate the Orobanches to germinate more. So genotype by type of host plant extract is we want to see if there's an interaction between genotype and the type of extract used to promote germination. That's what we're doing. And the way they set the design up is they have a bunch of plates, I guess like Petri dishes that have seeds from one of the treatment combination. And for whatever reason, there's different numbers of seeds on each plate. I don't know why they did it that way, but it's a completely randomized design. There's no blocks. The plates are not grouped in any way. There's just each plate is like its own individual unique thing. And there's an N for each plate, the number of seeds that are on that plate, and the number that germinated. And every plate has its own treatment combination, genotype and host plant extract type. A very simple experiment. Okay, so before we do any stat modeling, we're going to take a look and see what is so right, each one has a germ, the number of germinated seeds, and an N total number of seeds. So we're going to load the data. We're going to calculate the proportion, just make a new column in the data called P, which is the number germinated divided by the total number of seeds. And we're going to make a box plot, which we're going to look at each genotype and then color the box plot by the plant extract type. And I've defined this colorblind friendly color scheme, which I did that at the very beginning of the script because it's nice to use colorblind friendly colors, which you should do in all your manuscripts if you use colors. All right, so this fell asleep. Let's go back to what we were doing. And once I get that going again, I'll show you that. Okay, here we go. So we're going to load the data, hit Control Enter. Now Crowder Seeds is in our environment. We're going to define a new column, P as the germinated number divided by the total number, germ divided by N. And we want genotype to be on the x-axis, GEN. We want our P to be on the y-axis, proportion of germination. And we're going to group the box plots by the color, coloring them in with the extract type. And on this line, we're going to put geom underscore box plot, meaning we want to, the type of plot we want to make is a box plot. Hit Control Enter. Oh, I didn't run the previous line, so I'll run that line. And then, right, it didn't, that gave me an error because I forgot to create the P column before I made the plot of that column. And so there's the plot. You can see there is kind of maybe an interaction between genotype and host plant extract where the cucumber is more effective at promoting germination, and that it depends on genotype. So there's an interaction between genotype and extract type, because bean is ineffective at both genotypes. Cucumber is especially effective in one of the genotypes. So going back to the slides, well, what some people would do is, okay, let's just fit a linear model and use that proportion variable as the response variable. Our P, it's like it varies between 0 and 1. That's actually okay in many cases, because if the proportions are not too extreme, too close to 0 or 1, if they're like between, away from 0 and 1, your normally distributed error can still work out because there's a little room on either side for error to be without going outside of 0 and 1. And here you can see I'm going to do this in a Bayesian model. Our P is our proportion response variable, and the fixed effects, we only have fixed effects, genotype, asterisk, extract. That means genotype is a fixed effect, extract is a fixed effect, and the interaction between them also. And I've put a prior normal 0, 1. And that's actually an extremely uninformative prior in this case because proportion has to be between 0 and 1. So if I already have a standard deviation of 1 on the prior, that basically gives, because these fixed effects are categorical, that encompasses any possible effect size. So we're like basically not, that's completely agnostic. We're allowing for very extreme effects. Like if the coefficient is 1, that means it's varying, that means it's increasing the proportion by 100%, which is the highest it could possibly even do. So this is, it looks like a small number, but it's actually like, we're not assigning really any, it's basically a flat prior in this case. Although it is a little bit peaked at 0. So we're still saying there's a slightly higher probability no difference, but we're assigning a very high probability to any possible effect that we could conceivably observe. So let's do that. So this first part of it is the model formula. P is the response variable by, we can put spaces in between to make it more legible, genotype asterisk extract. Okay. Those are our fixed effects. Prior is going to be normal 0, 1, class equals B for the fixed effects. Betas are going to be the have prior of normal 0, 1. And then this is what data it comes from, a random seed, so we get the same answer every time, and this is where the previously saved model object is found. And then we hit Control Enter to run that. Yes, so the command stand path has not been set yet. I think that happens when this thing went to sleep. So I will have to set that again. This might happen to you as well. So I'll go back up here and copy this. And I'll just put this in here. Hopefully, so yeah, it's set. We have to use command stand r set. Okay, so that, yeah, you'll have to run that line again because this doesn't happen on a local machine, but for some reason on this remote server, whenever it goes to sleep and starts up again, it forgets where command stand is found. So you'll have to use that. And that should be in the chat as well. Yes, that's right. So someone was asking about seed. Seed means start the random number generator at a certain value. You can put any number here. I just put kind of like a random integer in there, that just means it's initializing the random sampler that's sampling the posterior so that if we run this multiple times, we'll get the same result. So yes, I usually use like the time of day whenever I write the code as the seed or whatever. Yes, so we'll reassign the path and then we'll run the model. Okay, so I will not look at the results yet. I'm going to compare them to what I think is a more appropriate model. What we're going to do is fit a generalized linear model to the outcomes. Now again, so we're not fitting a model to the proportions, we're actually fitting a model to the outcomes, the individual binary outcomes that we observed, which we can think of as being zeros and ones. 0, it didn't germinate. 1, it germinated. And the way you write that in the BRMS syntax is in this way. You have to write the variable that indicates the number of successes, the number of 1 outcomes, and then use a vertical pipe. And then you say trials, parentheses, the total number of trials. That is the number of seeds in the dish, including the ones that didn't germinate. If you look at the Crowder.seeds data, we'll put head Crowder.seeds, look at the data. You can see that, yes, each plate had a different number of seeds. Like this plate had 39 seeds, 10 germinated, and it tells you what the genotype and extract was for that plate. So this is their whole numbers, they're integers. The number of germinations and the total number that were in the plate, 10 out of 39. Okay, and that's how you're going to write that for a binary model. And here's the part that is kind of confusing. We have to, because it's a generalized linear model, we are not using a normal distribution anymore. We're using a different distribution. And the way you use that is the argument family in the BRM syntax. You have to say, what is the distribution function and what is the link function? So that's the response distribution. And what is the link function that we're going to use to go between the observed data scale and the model prediction scale? And here we're going to use binomial family with logit link. And binomial, I don't, if people are familiar with that, it's a statistical distribution that has two possible values, 0 or 1. Like if you flip a coin that has a 50% probability of heads, that the distribution of coin flips, heads and tails that you get is a binomial distribution with a parameter of 0.5. The probability of a success or of getting heads is the one parameter of that distribution. So a coin flip results over many times follows a binomial distribution with a probability parameter of 0.05. So that's an easy one, but what is the logit part? Let me explain what logit is. Well, as I just said, I think I said this a minute ago, if you take a linear combination of fixed effects and random effects, you're adding and multiplying numbers together that can be positive or negative. It can have any value, very high, very low. It's not bounded in any way. It could be positive or negative. But we're trying to model a probability. A probability cannot be any number. It has to be between 0 and 1. So what logit link function does is a function that takes unbounded values that could be anything, positive or negative, and transforms them or maps them onto a scale that ranges between 0 and 1. How does it do that? Like this. This is the function. Logit of a probability is log of p divided by 1 minus p. P is a probability, has to be between 0 and 1. But this actually, the log of p over 1 minus p can be between negative and positive infinity. This is what logit looks like. You can see the y-axis on this graph goes from 5 to -5, and it actually keeps going to positive and negative infinity, but the x-axis, the p, is only between 0 and 1. So it's taking any number you want. You can put any number you want, and it'll turn it into a probability between 0 and 1, basically. And you can also see that it's pretty much a straight line in the middle. When the probability is moderate between about 0.2 and 0.8, it's pretty straight. But then as you get close to 0 and 1, it just turns and goes almost straight up and down, which means, and the logit is also called the log odds, because p over 1 minus p is called the odds. The way I can conceptualize this is if you have an event that has an extremely low chance of happening or an extremely high chance of happening, a little increase or decrease to the probability will change the odds a lot. Like if the odds of getting into a plane crash is extremely low. If you increase the odds of getting into a plane crash, or if you increase the probability by 1%, that's making the odds many, many, many times higher, right? Because the probability is kind of low. But if you have an event that's 50% chance of happening and it changes to 51%, you've gone up by 1% probability, but the odds don't change that much. It didn't multiply the odds by very much. So if you have an extremely close to 0 and 1 probability, that's why the line is so steep. A little change has a big impact. That's logit. Well, and so let's do this GLM. We're going to put this germination by trials as our response variable instead of the p. We're going to put binomial with logit link as the response. And here we're going to use a prior with normal of 0 and standard deviation of 5. Why did I pick that? Because log odds scale, we're saying the mean is 0, so we don't have any. We want to say there's a 50-50 prior belief of one genotype having a higher mean or lower. We don't know before seeing the data which one will be higher, and we don't know before seeing the data which extract will have a higher mean either. We're putting 0 as the mean. But we're going to use default. No, I'm sorry. Yes, the standard deviation is 5 because that's actually a difference of 5 on a log odds scale is a huge difference. That's a 5 log fold change in the odds. That's a very, very big effect. So we're saying the mean is 0. We don't know which is higher or lower. And we're being very agnostic about whether it's a large or a small effect. We're giving a very wide prior on it, on the log odds scale, right? That only works on the log odds scale. If we had like a normally distributed variable that was measured in micrograms and was thousands or something, then 0,5 prior is actually very narrow, but on log odd scale, it's very wide. So you have to know the scale of your data before you set a prior. And someone asked, Bob asked, if a perfectly balanced coin were to turn a logit of 0. Yes, the odds, right, the odds is the ratio of one event to the other. The ratio of heads or tails is 1 to 1 if the coin is perfect, and the log of 1 is 0. Yep, and you can, Zach, helpfully put the math of that in. Yes, 0 is right in the middle. Just like 0.5 is right in the middle of the 0 to 1 scale, 0 is right in the middle of the logit scale because the logit scale is both positive and negative. Good question. So let's actually run this code here. Let's run the, we're going to fill in the model formula, the response family, and the priors. So we'll put germ is our number of successes, successful outcomes, and how many trials. Trials, parentheses, n. Yeah, it's always trials. That's the name, but this germ and n could be different depending on what the name of the column is in your data. Binomial is the distribution, and link equals, in quotation, logit. There's other links you can use. We're going to use logit. And the prior distribution on the fixed effect is normal with a mean of 0 because we don't know if it's positive or negative before we see the data. And standard deviation of 5, meaning we really don't know if the effect is big or small. We're saying there's a decent probability of big or small effects. So we're going to hit Control Enter and run that. And if you did it right, it will do it instantly because the model is already saved on this machine or this server. And so the way that you can assess in Bayesian world whether a model is a good fit to the data or not, right? We want the model to be a good fit to the data. If it's not, we shouldn't use it to make predictions. We want it to at least fit the data that was used to fit it. Otherwise, it's not going to be good at predicting other things. We want it to fit the data we used at least. That still doesn't mean it's a good model, but at least it fit the data that we used to create that model. Well, that's at least a necessary condition for us to be able to use that model to learn things about the greater world. So we can do this by using a posterior predictive check plot. What that does is it plots on the same plot the distribution of the data and the distribution and the posterior distribution of the predicted values from the model, the fitted values. If we want those to be very similar in shape to the data. So when we make one of these plots using the pp check function, it's going to give us a thick black line. That's sort of a smoothed out histogram of the actual data. And each thin blue line is a distribution of the predicted values from one random draw from the posterior. We have thousands of posterior samples, but we're just going to plot a few just to get a general idea. So we're gonna do pp underscore check for our linear model. We'll do that first. And here it is. So you can see that this is the data, and the thin blue lines are the posterior predictions. And it seems like, okay, it's reasonably good fit because the data kind of has a lot of values right in the middle at 0.5 and kind of not too many at the extremes, and so does the model predictions. Not that bad. pp underscore check Crowder GLM. We'll do that for the GLM as well. And here because our response variable was not the proportion, it was the number of outcomes. The x-axis is not from 0 to 1, it's from 0 to 60. And this is what the distribution looks like. And you can see that the model is like a decent fit to the data here as well. So actually, they're both a reasonably good fit to the data. But one thing you can see on the the regular linear model is that it's actually the posterior predictions are a lot of times going above 1 and below 0. As we mentioned before, that is a nonsensical prediction. So it's actually saying there's some of the fitted values are giving a probability of higher than 100% or lower than 0 of germination. So that's not, again, it can be a decent fit to the data, but still on the extremes kind of go off the rails a bit. Yes, and so again, why is it a problem? Because it's making predictions that don't make sense, which means that can affect our inference as well. And so what I wanted to do next to show that is we're going to use the model to make predictions. Prediction in this case is the expected probability of germination for each combination of treatment and genotype, extract and genotype. And we're going to use the EM means package for that. You may know about this package even if you don't do Bayesian stats, but it is like if you use SAS, LS means is a statement you put in your modeling proc to get predictions. EM means is kind of the same equivalent, R package. So we're making predictions for different combinations of treatments. And we can also do pairwise contrasts to see if there's a difference between those means as well. And the syntax here is pairwise by extract, pairwise contrasts of extract by genotype. So within each genotype, we're going to estimate the predicted mean for each treatment level and take the contrast between them. And that's the different, in this case, the difference between the proportions for our linear model of proportions. So so we're going to use the EM means function here on line 125. And we're going to say we want pairwise contrasts. We want contrasts between the two levels of extract. And we want to do those contrasts separately for each genotype. And hit Control Enter and run that. And then we're going to also do that for the generalized linear model. Same syntax, except it's going to give us, yeah, so in the linear model, it's going to give us a difference between the proportions. In the generalized linear model, is going to give us the difference of the logits of the log odds of the proportions. That may not make sense, but we'll show you what that means in a second. So if you let's first look at the linear model predictions. We're going to look at the EM means object inside of this here. If we hit Control Enter, you can see here are the mean proportions that this linear model estimated. It said, well, our mean, for example, for genotype 073, our mean posterior estimate is 33% germination probability with a 95% credible interval going between 19% and 47%. Great, what's wrong with that? And if we look at the contrasts, there, you can use $contrast to pull out the contrast object from that. Hit Control Enter. You can see here are the difference. So for this genotype 73, there's a 14% difference in the germination probability. And for genotype 75, there's a 34% difference. So that seems fine. It doesn't really, again, why do we need the generalized linear model if our linear model is giving us a reasonable answer? Well, I'll get to that in a minute. Let's make the same prediction for the generalized linear model. Again, we want pairwise contrasts of each level of extract within each level of genotype. So we're going to hit Control Enter on that. And run the EM means. And again, so it says results are given on the logit, not the response scale. So the log odds of germination in bean, extract, and genotype 73 is minus 0.418. What does that even mean? I don't really know. I don't have an intuition for it, right? So people will not understand that either. What you have to do is usually transform your estimates back into the data scale to make them interpretable. And so let's do that. We're going to use a new argument. I'm going to do this again, the same EM means with extract by genotype, but I'm going to use type equals response. And that will take the means and take them back from a log odds scale, which no one can understand, back to the probability scale where they're between 0 and 1 again, and you can understand them. So hit control, but because the model was fit on the logit scale, we're never going to get bad predictions. The uncertainty is always going to be between 0 and 1. We've just mapped it back to the scale that we can understand. Type equals response is how you do that. Now we look at the EM means. What do we get from the generalized linear model? These are our estimates. You see they're all between 0 and 1. Those are the different probabilities we estimated and their confidence credible intervals. The contrasts, we hit Control Enter here to see the contrasts. Now, we don't get a difference in probability anymore. What we get is an odds ratio, and that is the ratio of the odds of two events. So in genotype 73, the odds ratio, bean versus cucumber, is less than 1. That means bean has a lower odds of germinating than cucumber. And here for genotype 75, the odds ratio is even smaller. So the difference is even further from a 1-to-1. And we can see that when we look back at the data here. In the data, the difference on genotype 75 was a lot bigger. That's why this odds ratio, bean versus cucumber, orange is bean and blue is cucumber, is even smaller. An odds ratio of 1 means no difference, 1-to-1 odds. But here is the further away from 1 you get in either direction, the bigger the effect. So that's what that is. Does anyone have any questions on that? So we have, as you can see from my scroll bar, we're kind of like 2/3 of the way through our lesson today. I have a few more things to show you about this model, because now that we have the model, I'm going to show you how you would make predictions and present them in a paper. And then we're going to do one more example data set today. So I think we should, I'll take a break after we get done with this model for another few minutes. And then I would say it will take, 45 minutes or so to do the remainder after that. So we should be done with everything in an hour, I think, if that's all right. But feel free to, quit out early if you have other things to do. Going back to the slides. Yes, so I showed you how to transform the results back to the data scale. And once again, this is just an explanation of the odds ratio, which I've already been through again, so I'll skip that. Now, basically, that is all you really need to present, is the model predictions, the predicted contrasts, and their credible intervals, showing there's evidence for a strong evidence for a difference, right? Like this, the odds ratio on bean to cucumber in genotype 75 is 26%, basically meaning that the odds of germination are 4 times lower, or only 25% as big in beans versus cucumbers. And our credible interval is between 0.18 and 0.36, meaning there's 95% posterior probability that the true odds ratio is between basically 0.2 and 0.3. So we have very strong evidence, at least for genotype 75, that there's a difference in this germination rate. That's all you really need to say. Like, why would you test a null hypothesis? Like, what's even the point? Null hypothesis doesn't mean anything anyway. It's, hypotheses that something is exactly 0 is never going to be true anyway, because nothing in reality is exactly 0. There's going to be some difference. We're just trying to estimate how big that difference is and how certain we are about that difference. To me, that's all you need. But if I'm a journal editor or a reviewer, and that still is not as enlightened as we are, they say, well, you have to test a null hypothesis because that's how everyone does it. So that's fine. We can do that because, you know, we're only doing Bayesian statistics for practical reasons, not because we think null hypotheses are, you know, wrong or whatever. So we can do that. So I want to show you how to do that because a lot of journals would want you to, and people also find it more intuitive because that's what they're used to. Oh, I see a question. Do you have any recommendations for textbooks or online courses in Bayesian statistics? Yes, I have it. I actually brought it in this book. I'll show you. Basically, if you only want to read one book, you should read this one, which is called Statistical Rethinking by Richard McElreath. I have the link to the page for the book, which also he, all the chapters, he also recorded video lectures for all of them. So you can go, basically this is like what I wish I could do if I had more time and was smarter. I would just do this, but you're just getting like, you're getting me because I'm not as good as Richard McElreath, but you should definitely read this. Yeah, all the information is on the course website. There's a page for external learning resources that has all the links you need to get access to this. Yeah, so that's my recommend. I have other recommendations as well, but that's I would say the best one if you had to pick one, to a desert island. Yeah, so let's say we want to do null hypothesis test. Well, we are going to refer to this useful resource that I really like called the Bayes test R package, which has a function called describe posterior, which basically is like an all-in-one function that will give you means and quantiles of your posterior distribution, as well as calculating those Bayesian p-value style numbers that we already went over, the p-map that we talked about a minute ago. And so what do we want to do? Well, let's use this Bayes test R package. Let's use that linear model that just modeled the proportions and look at the differences between the means of you know, the proportions. Or let's use it for the generalized linear model for the odds ratio. And what I'm trying to demonstrate here is why the generalized linear model is better and why we should use it as opposed to just modeling proportions. So hopefully this will help show that. So again, I didn't mention this because we're just using the default, but by default in BRMS, you can change this, but by default, it samples 4 Markov chains to sample the posterior distribution. And by default, it samples 1,000 samples from each chain. So you get every parameter in the model is characterized by 4,000 values. It's like a vector of 4,000 values that are samples from the posterior distribution of that parameter. And so, you know, if you could make a histogram of it, it would show the shape of the parameter distribution. And if you use describe posterior we want to learn something about that posterior and use it to make inference. Well, first it'll say, well, what's the point estimate? What's the median of that distribution of those 4,000 numbers? And what are the quantiles? We want the equal-tailed credible interval, which means we're going to take basically the 2.5 and 97.5 quantile of those 4,000 numbers, equal-tailed because it has equal number on the outside on both sides, and that'll give you the credible interval. By default, it gives you 95%, but you could use other numbers. We're still kind of using 95% because of tradition of 0.05 p-value cutoff is still a strong tradition. So people still usually use 95, but there's no reason to use 95 because we're not doing null hypothesis testing necessarily. But now again, we're going to use this p-map value again. And because I also want to show there's not really any consensus on what the best Bayesian analog of a p-value is. We're going to also calculate a different one called probability of direction. So we're going to use this p-map that I explained before, and we're also going to use probability of direction, PD, which is how much of the posterior distribution is on one side of the null value, basically. So like if all 4,000 values are greater than 1 for the odds ratio, the probability of direction will be 100%. We can say there's 100% posterior probability that the odds ratio is bigger than 1, and vice versa. But if the posterior is kind of on both sides of that, it'll be less than 100%. And we specify null equals 1 for the odds ratio because, as I said, in odds ratio, 1 is actually the null value because 1-to-1 ratio means no difference. So we're going to say null equals 1 for this contrast in the odds ratio contrast. So let's do that for both models. So we're going to use describe underscore posterior for the linear model where we just compared the portions. We're going to use ETI, equal tailed interval, and we're going to use PD and P underscore map as the tests. We're going to do that for the linear model. And for the generalized linear model, it's all the same, except you also have to add null equals 1. Okay, so let's run. Okay, so here's the for the linear model where we just compared the proportions. These are our P map values. And for the, it says, well, there's sort of not very much evidence that there is a difference here. There's more evidence, there's a difference here. And James also asked about the Bayes factor. That is another similar Bayesian analog to a p-value that looks at evidence for the posterior versus the prior. The reason I avoid using Bayes factors is because they are very sensitive to what you chose as your prior distribution. So you can really, even if your results are not sensitive to the prior, the Bayes factor still depends a lot on the prior. So if you use a Bayes factor, you can kind of like, yeah, it's very dependent on the prior, and I don't think that's necessarily a good thing. So I try to avoid the Bayes factor. And I think most people in the literature are getting away from the Bayes factor as well for that reason. So now let's do the same thing for the, but the P map and P direction do not depend explicitly on the prior. They just depend on the posterior. So they're not as sensitive to the prior. Yep. Yeah, so let's do that for the other model as well. Well, we actually have, you can see that there's actually lower P map values and the P direction values are closer to 100%. So this kind of has an opposite interpretation. In P map, lower is more evidence. P direction, higher is more evidence. This generalized linear model actually has more power basically than the model where we're comparing the proportions. It was able to kind of detect these differences better and has stronger evidence based on the generalized linear model. You can see this one is less than 0.01. And this one is 0.055, or it was only 0.33 in the linear model. And why is that? I think I have a slide for that. Basically, if we just do the model on the proportions, we're throwing away information. We have a lot of seeds in each dish. Those are not all independent because they're from the same dish, but they're kind of partially independent. And if we had, let's say we observed 200 out of 1,000 versus 2 out of 10, well, I'd say 200 out of 1,000 is giving us more evidence that the true probability is 20%. So you should have greater precision in your estimate there. But that information is thrown away when you're fitting the linear models of the proportions. That's why it's better in this binary case to use the generalized linear model. That's why it has more evidence for the difference. Yes, and so we also said, is there an interaction between genotype and treatment, right? If you look at the thing, here's like not a very big difference, here's a big difference. We see the odds ratios are different. We could actually test the hypothesis formally that they're different by taking basically the ratio of the ratios to see if there's evidence that these odds ratios are different from one another. Is this ratio of 0.27 different than this ratio, which is only 0.57? We can actually take the ratio of the ratios. That's how we would do that. Well, let's see, where was I? Yep. You have to, it's kind of complicated how to do that, but you can do it with two levels of contrasts called interaction contrast. And you have to specify, in this case, we're doing reverse pairwise so that the, basically so that the higher number will be on top, and that'll show us if there is a evidence for an interaction between genotype and treatment. Is the treatment effect different between the two genotypes? So we're taking contrast and we're contrasting them with each other, basically. And then we're going to do the same p-value analogs and equal tail credible intervals that we did with the other stuff. So we're going to do a contrast on this, and we're going to do interaction contrasts. So take a contrast and then contrast it with another contrast. And then we're going to describe the posterior. So yeah, we're doing a hypothesis test if these two numbers, basically this 0.57 and this 0.27, are different from each other, because you might want to know about that. Now we'll run this, and you can see basically, yes, there is strong evidence they're different. The ratio between them is of genotype 73 to genotype 75 is 0.46, and the credible interval is basically far from zero. So we have strong posterior evidence that there is a difference, and we can see that from our p-value analogs as well. So that might be something that you would want to put in a paper, for example. So basically, I wanted to, that's all I have for this. Before I go into how to write this up in a manuscript, does anyone have any questions? Yeah, so since people asked about this in the last lesson, I wanted to describe how to report this in a manuscript. So don't worry about the code for the figure and table. I just want to give you an example of how to do it. It's kind of sophisticated code, so we can go over it in more detail in office hours if you want to. So first, I want to say how you would verbally write up the stat model and put in the methods, and what you would put in the results. Oh, but yes, I do have a question from Kip. Why did I use the particular prior that I did in the generalized linear model? Because it was normal with a mean of 0 and standard deviation of 5. Okay, the reason I chose normal is because we don't know whether the treatment will have a positive or negative effect. So normal allows both positive and negative. We have a mean of 0, meaning we're saying it's 50-50 if the effects of treatment or genotype are positive or negative. So that's why there's a normal with a mean of 0. Why did I pick a standard deviation of 5? Because we are doing this model on the log odds or logit scale, and that a difference of 5 on a log odds scale is a very, very big effect. So we're saying we don't know if the effect is positive or negative, and we're very uncertain if it's a small or big effect. We don't want the prior to influence the results as little as possible. So that's why we use 5. Yeah, office hours. So after we get done with this, at around 12:30, I'm going to take a lunch break and then get back on the Teams. If anyone has any questions this afternoon, I'll be on there for a couple hours on office hours. Yes. I forgot to mention that earlier. So yeah, this is the last thing we'll do before we take a break. This is kind of what I would write in the methods of the stats section of the methods for if I was going to put this in a paper. Basically, we want to say what kind of a model it was. What are the predictors, the fixed effects in the model? Since it's a generalized linear model, you need to specify what is the distribution and link function. This stuff is kind of like standard language I always use for Bayesian models. Actually, I did not do this with you all, but you should always verify the model convergence with the convergence diagnostics. I'll go over that later, I guess. I'll do that in the next model so you can see how to do that. And we looked at the posterior predictive check plot as a graphical check of model fit. And then I explained, okay, what predictions did we make from the model? We got the means for every treatment combination, and we took the odds ratios. And then we say, well, how did we? So that says those are our posterior estimates, and then this is kind of explaining that we use credible intervals and then those Bayesian p-value style numbers to get the evidence, how much evidence there is for differences between the extracts. So yeah, basically this has all the elements. It's got like what model was fit, any details on the sampling procedure, and what predictions were made and how you tested any hypotheses that you have. That's basically, this is like the general outline of what you want to put in the methods. And then what would you put in the results? Usually I would try to put the posterior median estimates as well as the credible intervals for anything that you, any quantity that you're trying to talk about. And then I said, well, this is like the ratio of the two odds ratios, which we got that 0.46. Here's the credible interval, and Bayesian p-map value means that we have evidence for that cucumber extract has a greater effect on germination probability in this one genotype compared to the other. That's how I would usually do it. So yeah, usually I try to not just put one number for the point estimate, but also put the credible interval boundaries in there as well in brackets, so that people can see the uncertainty around the numbers. Okay, and the figure, well, what I like to do, I'll just show you the output kind of, and I didn't put this code in the worksheet, but I'll copy it and paste it in to what I'm doing. What I usually like to do is show the point estimate and not just show the 95% credible interval, but also show some other ones so you can get a better sense of the distribution. Yeah, basically there's a package called Tidy Bayes that it makes it easy to pull out these draws, posterior estimates, summarize them, and make plots. And I had to back transform the means from the logit scale back to the probability scale as I did that using this line of code. So I'll copy that and I'll paste it in here so you can see what that looks like. Yeah, so this is kind of like what I would show. You can see here are the dots are the medians, and then we have different colored intervals for the different, I put the 95, 80, and 50% intervals. So I think that looks nice. And it's colored by the extract. And I also, that just shows you the general information you'd want to put in a figure. And then for a table, yeah, I had to do a lot of rearranging of the data to get a manuscript quality table. But again, I use the Tidy Bayes package. There's a function called median QI, which gives you the median and the quantile equal-tailed credible interval from a posterior distribution. And I've basically taken gotten the germination probability for all the treatment combinations and the odds ratios as well, and put them all in the same table. And I use the GT package to make a very nice table. That's a really good package that that you can use to make tables that are good enough to go in a manuscript. So I'll just run all that just to show you what you'd want to use. Yeah, so this here you can see in the window, the table pops up. I've got my, for each genotype and treatment combination, the germination probability with a credible interval. And then I have the odds ratio between the two treatments for each genotype with a credible interval. That's the kind of table I would want to put in a manuscript. That kind of summarizes the model output. Yeah. Any questions on that? Great. So why don't we take another 10-minute break? And yes, we've done most of what we want to do today. I have one other example, which is another generalized linear model that would, we still have time to go through. So I'm gonna stop here. We'll start again in 10 minutes at 11:53 Eastern, 10:53 Central, and we'll go through our last bit of stuff for today. Then we'll have a lunch break, and I'll come back for office hours. But I'll I'll just answer questions now too. But we'll take a break for 10 minutes. I see Mahesh has a question about, yes, you can. For the GT table, there is a function that allows you to export it to a Word document. So you can include in your script pipeline it'll export it to Word. And for LaTeX, that the GT package isn't really good for that. There's other packages that will format it for LaTeX for PDFs and stuff. I don't think GT can do it. You'll have to look. What's the name of the one that there is a package that does it for PDFs. I can't remember the name off the top of my head, but I will look it up and get back to you on that. I think it's, flex table is what I'm thinking of. You should look up flex table. I believe that will, it has different syntax, but it can do, I believe, output things in LaTeX format. Flex table. Yep. Let's see, I should. Let's mute the mic here.
I see there's a question Zach asks, is there a risk for the generalized linear model? Is there a risk when interpreting contrasts as difference in probabilities rather than as their ratios? Yeah, I mean, some people say it's fine to interpret it as a difference in probabilities and not odds ratios. It's kind of a different, interpretation, right? Like it's, if your probability goes from 1% to 2%, you know, that's an increase of 1%. If it goes from 51% to 52%, that's also an increase of 1%. That would be considered the same difference of if you're adding and subtracting probabilities. If you're doing it as ratios, right, 1% to 2% is doubling the probability versus the 51 to 52% is hardly changing the probability at all. So it's a different yeah, it kind of depends on your interpretation. Yep. So just, yeah, knowing the odds ratio is does kind of depend on where you start at. But I guess the reason why it's better to do odds ratio is, let's say you're like, okay, we've determined that this like new treatment decreases the probability of disease by 10% every time. It's like, well, what if your probability of disease is only 5% to begin with? Then that doesn't mean anything. It can't decrease it, you know, by 10 because you're already at 5. But you can always have an odds ratio. Like no matter where you are, you could always say it decreases the odds by a factor of whatever. It'll never go into negative or above 100%. So that's why odds ratio is more general than like could never lead to a estimate that doesn't make sense. But yeah, within the context of this little experiment here, like I think it would be fine to also show them as additive difference in probability. There's no reason not to there. It just depends on your question, basically. Yeah, I mean, statisticians like odds ratio because it has nice statistical properties, but like in real life, people don't really understand it. So like you can go back to just like, what's the difference in the probabilities? And another question from Alexandria, when would it not be appropriate to use generalized linear models? Well, if you have data that are where it has normally distributed error, then just go with that, you know? That's like the nicest. Normal is like the easiest distribution to work with and has nice properties. So like if you, right, like I said, like if it's just like, you know, if you're measuring weights or some property like that, that's like the mean is the most common value and then some are a little higher, some are a little lower, then is a normal distribution is going to be a great approximation. And so it'll be fine to use that. And plenty of data follows that. So there's tons of times when you can just go use a linear model and not have to use generalized. I mean, it's very common. It just depends on the type of data you're working with. Yep. Some fields have more nice normal data than others. So we'll start back up again in just a minute. Knock out the last example. No, it's been a lot already. Yes, yes, I see there people talking about odds versus probability. But actually, Brad, odds of 8 successes to 2 failures is not odds of 0.8. That's actually would be called 4 to 1 odds. So it's like an odds of 4 or 1 in 1, 2, 4 if you're doing it the other. Yeah, like probability is however many out of the total. Odds is, 1 to 1 is like 50%. So like a probability of 1/2 is the same as like 1 to 1 odds. I kind of have trouble thinking in odds too. It's people that like gambling do, but other than that, I think probability makes more sense. Anyway, yeah, great discussion though. Well, I'll, in the interest of time, we'll just knock out the last example here in a half an hour and then have a lunch break and then have office hours. So the last example is going to be different from the other one, number 1, because it's now a mixed model, which means we're going to have some random effects because the experimental design requires it. And also because we're not going to use binomial distribution anymore, we're going to use a different response distribution, which also is very common in real life data. So I just mentioned it's now a mixed model. It has a mixture of fixed and random effects. Well, generalized linear mixed models require dealing with very complicated integrals. Computationally, it's hard. And Bayesian works a lot better than frequentist to get the answer because it can use that little extra bit of information from the priors that help constrain the estimates to actually get an answer where the maximum likelihood of the frequentist methods don't work. So yeah, most of the time that I'm using Bayesian stuff, it's dealing with generalized linear mixed models. And yeah, in the syntax is very similar to what we've seen before, except instead of just having our fixed predictors on the right-hand side of the model formula, we now have some random effects as well, like blocks in an experiment, like a randomized block design experiment. And we still have to do our response distribution and link function, just like we did just now. It's still a generalized linear model, but it's also mixed, so we have random effects. We're going to use a agronomic data set that's in the AgriDat package again. It's looking at turnips. I guess everybody loves them. They are looking at the yield of turnips and yield, right? It's a continuous variable, but it is not necessarily following a normal distribution because it has to be 0 or greater, right? You can't have a negative yield. It's going to be 0 or greater. And if you, yes, that could still more or less follow a roughly normal distribution, but what if you have a lot of yields that are 0 or close to it and a few high numbers, then it's going to be a skewed positive distribution. And those are very common in ag science, I think. Yeah, I see lots of yield distribution that is not symmetrical. It's going to be skewed a lot of times. So let's take a look. Let's go back to our console and take a look at this example data. I'm going to load the data with the data function, and then we're just going to make a histogram of geom histogram of the yield. So we're just going to say one variable x equals yield is the only thing we're going to plot, and we're going to make it a histogram. So we're going to load the data here. And then we're going to say x equals yield is the only variable we want to plot. And geom underscore histogram is the type of plot we want to make. Yes, so just like I said, it's a skewed data. Some are basically almost zero, and we have a few high numbers of yield. This does not look like a nice perfect bell curve, right? It's very skewed. And the yield data that I just showed you comes out of a experiment where they had 3 factors and looked at all possible interactions between them. There was 2 genotypes of turnip, Barkand and Marco. They had 2 planting dates. One is a little earlier, August 21st, and one is a little later, August 28th. So two levels of genotype, 2 levels of date, and they have 4 planting density levels, 1, 2, 4, and 8 kilograms per hectare. So we have 16 combinations, 2 times 2 times 4. And they took all 16 of those combinations and planted a 1 plot of each of them. And that's a block. And then they replicated that block 4 times. So it's called a complete block design because every block has all the combinations. And it's randomized complete block because you mix up where in each block the combinations go so that there's not any confounding effect there. And so you got 64 data points, 16 plots and 4 blocks of them, and or 16 plots per block. And they took 1 measurement from each plot. They just said, what is the yield? That's it. And I'm going to modify this data set by converting density into a factor variable. We're not going to try to think about if like, there's some linear relationship between density and yield, like is the 4 kilograms per hectare 4 times the yield than the 1 or whatever. We're just gonna treat them as 4 discrete levels. So maybe it could, the 1, 2, and 4 could be the same, and 8 could be higher or something. We're not going to worry about the treating density as a continuous variable. We're just going to treat it as categorical, which we can get away with because there's only 4 levels. So we're going to change it to a factor. That's how you do that. A factor is a categorical data type. We're going to turn it to a factor. So make sure you run this line, because if you don't, the model will be different than what I'm going to get. So definitely, if you don't have to make all the plots, but definitely don't forget to run that. Okay, now just to take a look at the data before you fit the model, we're going to make a box plot of yield in each treatment combination, and we're going to density, the planting density is our X variable, yield is our Y, and we're going to group the box plots by every combination of density and date and color them in by date. And we're going to make each genotype on a different panel. So we're going to show all 16 combinations on one crazy plot. That's how you do that. Let's see if I can remember what I did. So density on the X, yield on the Y. Density on the X-axis, yield on the Y-axis. Grouping them by combination of density and date, and coloring them in by date, and make each genotype on its own panel. And then we'll take a look at what does that look like. So what do we see? Well, I can see here that there seems to be interaction between planting density and planting date, where like at the early planting or the low planting density, the yield is about the same regardless of planting date. At the high planting density, there's like a higher yield at the later planting date or whatever. And maybe there's a bit of a interaction with genotype as well. The basic trend is there for both genotypes, but maybe there's a bigger difference here than here. You could say maybe from looking at the data. Well, this is just some example data, so maybe it works out very neatly, which maybe you wouldn't see this in real
real life, but I mean, technically this is real life data, but they picked it out to illustrate a point. So we have, oh yes, and something else to note. Yes, not only do we see these interactions, we also see a relationship between mean and variance in the data, right? Like here in the low yield, there's very little variation. In the high yielding, when the mean goes up, the variance also goes up, right? Like here, the higher the mean, the bigger this box is. What are the units of yield? I honestly don't know what they are. You can, well, yeah, we can look in the documentation of the data set, Conway.Turnip. If we put question mark, we can take a look and read if we can see anything about that. Yield. Yeah, it just says yield. So it doesn't even say what units. You'd have to go into the literature for that one. I didn't track that one down too far, but a good question. You know, maybe it's tons per hectare or whatever. So yes, the problem with this is if you, again, people were asking when is it appropriate to use generalized versus not generalized linear models? Well, a linear model, normal distribution, assumes the same variance for every group. Just like in your classic ANOVA, you have to assume homogeneous variance in groups. It's saying there's one standard deviation parameter for the entire data set that holds across all the groups. The residuals are supposed to be the same in this group and that group. Well, clearly they're not going to be if we do a linear model, right? The residuals in this group are going to be real small, and these ones are going to go up, have some high positive and high negative residuals. That's going to cause biased results that may give us the wrong conclusion. So that would be a reason, well, we probably shouldn't use a linear model normal distribution here because of the fact that the mean and variance are related. You can see that from looking at the data. But let's say we don't care about that, and let's say we're just going to do a linear model anyways, and say, well, hopefully it's close enough, and the unequal variance isn't a big issue. So let's try it. We're going to do a mixed model, but it's not going to be a generalized linear mixed model. It's just a linear mixed model. And here's how we're going to do it. We're going to put yield as the response variable, genotype times date times density. That means all the main effects, all the two-way interactions, and all the three-way interactions are going to be fitted in the model. Every combination of those three predictor variables. And this parentheses 1 pipe block means we're going to fit a random intercept. 1 is an intercept, and block means what is the group that's each going to get its own random intercept. So this means every block gets its own random intercept. And okay, again, what are we going to pick as the prior? So I've also generally based that off of the range of the data, which varies between 0 and 25-ish. So I'm using 0, 5 as a prior on the fixed effect. So I say, well, if you know, yield is like in this order of magnitude, any treatment that can cause the yield to change by 5 is a very big effect. So we're saying if mean of 0, again, we're being agnostic about if a particular treatment will have a positive or negative effect, but also the standard deviation of 5 means we're assuming there's a pretty big prior probability of large effects, right? Because a normal distribution has 2/3 of its mass within one standard deviation of the mean, and it has 95% of its mass within 2 standard deviations of the mean. So that means we think there's basically a 95% prior probability that the effect will be somewhere between -10 and +10. That's what a normal 0, 5 prior means. So this is a very uninformative prior in this case because it's assuming that we have a wide range of effects that we think are pretty similarly probable. Some are near 0 and some are large. We don't really have a strong belief on that. So this will not have a strong influence on the results. Again, we're kind of allowing the data to drive the bus here. That's how we're going to set up the model. So let's type in all of that. Genotype times date times density are our fixed effects. And our random effect is 1 for a random intercept, pipe, block. We're going to give each block its own intercept. And the only other thing to put is this normal 0, 5 prior. That's it. So now we can run that. And we will look at the posterior predictive check plot by using pp_check. Okay, so this doesn't show up too good on my screen. Hopefully you can see it better on yours. Here is the data, right? It's that skewed distribution we saw. We made the histogram. And here's the model predictions. Well, they don't really match up too good because the data has this, the model predictions do follow the skew a little bit, but we're missing out. We're not really capturing the shape of the distribution of the data all that well. Not to mention, look how much of the posterior predictions are negative, and we can't have negative yield. Because again, because the distribution of the data is skewed, if we assume normal distributed error, some of those predictions are going to be negative because it's trying to make a symmetrical distribution where it's really skewed and it's going below 0. That's not good. Yes, I'll skip that for now. So yeah, what is our model getting wrong? We just showed that it's kind of not capturing the shape of the distribution and it's giving us some values that don't make sense. So we can also, let's look at the estimated marginal means. We have other factors in the model, but we're just going to look at density for right now for simplicity. We're going to look at the means for each density level. So we just put the tilde density. If we hit Control Enter and run that, you can see that, yes, in particular for the planting density 1, the credible interval has a negative lower bound. So it is saying there's basically a 95% probability that the average yield for planting density 1 is between -0.6 and 4.6. And we know that negative probabilities, or I'm sorry, negative yields are not possible. So this is sort of a nonsensical interval. That's not good. Yes, I see Kip, Grant has answered Kip's question. Hopefully that answers your question, Kip. But the question was whether what does class equals B indicate on the prior? And yes, that is, the model has different classes of parameters, and you can put parameters on random effect variance components and stuff like that too. But I usually just go with the defaults for those. But what I usually do change the priors on is the fixed effects. And in BRMS syntax, B is what the fixed effects are called. And because yes, B is the name of the matrix of fixed effects in statistical notation. So that's why it says B. Yes. Some Bayesian do not like to use the term fixed and random effects because in Bayesian models, all parameters have a random distribution, posterior distribution. Some don't like to use fixed and random. I still use those terms because people are familiar with it. But BRMS does not use the term fixed and random effects. That's why it doesn't say fixed in there. Yeah, so good question. Okay, well, again, we're going to say, what is the old school way to deal with this skewed data? Well, a lot of people, and myself included, would just log transform the data and then fit the model, because log transform is great if you have positive and right skewed data. Because first of all, it ensures that all the model predictions are going to be positive. Because if you back transform back from the log scale, you're taking e to that number, that's always positive. E to the x is always positive, so you can never get a negative prediction. So that's good, because we know our yield can't be negative. Another reason to use log transformation is it is a variance stabilizing transformation. That means it gets rid of that relationship between the mean and the variance. It's going to make the variance within each group more equal, which is what we want, because we said that we don't want there to be a relationship between the mean and variance. So all you do to do that model is the exact same syntax as we had before, but we're going to put log parentheses yield as a response variable, not just yield. And I changed the prior to only have a standard deviation of 2, because again, we found that yield varied between 0 and 25 on the untransformed scale. On the log scale, it only varies by 2 or 3. So 2 is a large enough standard deviation to encompass very large differences on the log scale. So I've changed the prior to accommodate the new scale of the data. So the only thing I've changed from the last model is I put log around it, and I've made the prior a bit narrower to reflect that the data has a different scale now. That's all I've done there. So yes, I've left those 2 things blank. Log parentheses yield is our response variable, and the prior has a standard deviation of 2. Run that. Let's look at the posterior predictive check plot. You know, that looks a lot better, right? The data is pretty much symmetrical now that we've done the log transformation, and the model predictions, the blue lines are right on top of that black line. That means the model's a pretty good fit of the data. Also, you see that the x-axis goes negative and positive, which is fine on the log scale, because if we back transform that, they're all going to be positive. E to any number is positive, so we're good there. Or e raised to any power. Okay, and yeah, so that's that kind of solves our problem, right? Like, we've done a linear mixed model with the transformed data. That isn't that good enough? Like, why do we have to do anything more complicated than that? Well, there is a potential issue when you transform and back transform. It introduces a bias in the data or in the values. And it is better to, instead of transforming the data and fitting a model and back transforming, it's better to just pick a response distribution that actually fits the data and keep the data on its original scale. And that will not give you that issue of bias. So the distribution we're going to use here that works really well for positive right skewed data that we have is gamma distribution. So here are some examples of gamma distributions with different parameters. Now, you know, a normal distribution, no matter what parameters you put for the mean and standard deviation, is always symmetrical, is never skewed. But gamma distribution can be skewed. You see how this yellow one sticks out much further to the positive end than it does at the negative end. And especially this red one is very skewed. And it can never go negative. Gamma distribution cannot go below 0, but it can be skewed, just like our yield distribution. Also, gamma distribution has variance that's proportional to the mean, which is also good for our case. That is what we want. We want the variance to increase with the mean. We want to model that because that's a pattern we see in the data. So we want to pick a distribution that can model that. And that's what gamma can do for us. Yes, if you go back to the plot of the data, right? The variance is low here with a low mean. Variance is high with a high mean. We can pick a distribution that actually has that property, and then it will fit the data better. So this is very similar to the previous one. This is the GLMM. We're not doing any transformation right here. We're just putting yield as the response variable again. But the response family is gamma. It has to be capital G, gamma, and log is the link function now. So we're using log as the link function, so it's not that different than log transforming the data. But since we're doing that transformation within the model, instead of doing it in the data and then
and then it doesn't have the bias because it's all done within the model. It doesn't introduce any bias. So we just use yield as the response variable, no transformation. The family is gamma, capital G, and link equals log, put it in quotes. And we're going to use a normal prior with the 2 standard deviation because, again, because it's a log link function, we're still looking at the effects on the log scale. So 2 is a big effect there. That's our GLMM. Okay, let's run that. And then we're going to do the posterior predictive check again. Okay, so here's the gamma distribution. You can see instead of having to make the data look symmetrical, look like a normal, the distribution actually of the model is actually following what the data looks like. You can see we're keeping that skew in the data, and the model predictions are also following that. So we've actually, instead of forcing the data to fit the model, we've just got a model that fits the data, which is better. That's kind of what we want. Oh yes, I mentioned before, I forgot to tell you that whenever you run a Bayesian model, you should check whether it converged. And one way to do that is by checking the R hat statistic. And for these Markov chains, the closer that number gets to 1, that indicates convergence. As R hat approaches 1, the model converges. So we can use the R hat function on this model. Here, I'll put that in a R hat of GLMM. I'll make that into an object. And so this R hat GLMM gives you the R hat statistic for every parameter in the model. If we look at it, you can see, yes, all of them are like very close to 1, 1.001. Usually I use 1.01 as a cutoff. If all of them are below 1.01, I feel good. And these are all well below that. Yeah, you can see all the model parameters too, which is interesting. These are all the fixed effect parameters and the standard deviation of the block variance and the random effects for each block. They're all the different parameters, and there's a few others as well, for the shape parameter of the gamma distribution and the LP, I forget what that is. Yes, so anyway, those are we know the model converge, which is good. And we've seen the posterior predictive check looks good as well. Now, the rest of, I'm just going to go through the last couple slides to show you how to make predictions from this model, just like we did from the previous ones, and present them. So what we want are the marginal means for each. Now, marginal means has a different meaning in the context of a mixed model. This is the marginal means for every combination of fixed effects in the model, and we're basically setting the random effects to 0. This is like the prediction or expected value of a block that is smack dab in the middle. It's not a block with a higher mean or lower mean. It's like it's setting all the random effects to 0. That's what people usually do when they're making predictions from a mixed model, is use these marginal means. Essentially, the random effects do account for the variance in our estimate, but for the purpose of the predictions, we're kind of pretending the random effects don't exist. We want the prediction assuming there's 0 random effect. Just like it's sort of like the difference between if you say, well, the average height of a man in the United States is 5'9" or something, then that's that has a very narrow prediction interval because we're very sure that's the average height. But if you took a random man from the United States and got his average height, it would probably not be 5'9" because there's a lot of random. We know that it's a very wide distribution, but we do know that we're very confident about what the average is, but we don't really care necessarily about the random variation if we're trying to make a prediction on the average level. just like we don't really care about the block variation, which is just an experimental artifact when we're making predictions from this experiment. So we're going to get these estimated marginal means for every combination of treatment. And we're going to say type equals response, which will put the predictions back on the data scale, not the log link function that we used. So let's do that. So we want every combination of density plus planting date plus genotype and type equal response in quotation marks. Run that, and then we can run this line to print the print it. So yeah, we don't need to go through everything here, but these are the estimated means of yield on the original scale of the data with their 95% credible intervals for each of the treatment combinations. That's how you would get them. And what if we wanted to do contrasts? Well, let's say, for example, we wanted to contrast the density levels to each other for every combination of planting date and genotype. So it's like, okay, within this barcant in August 28th planting date, so like the 4 blue boxes here, what are the differences between their yields, comparing these 4 to each other? And because this is a log scale model, the contrasts are given as ratios, not differences. So like if one yield is 10 and the other is 5, the contrast is going to be 2, not 5, 10 to 5. That's the difference is multiplicative. And I put reverse pairwise contrast so that the higher density would be in the numerator of that ratio. So we want to do this, we want to do contrast. We want to do reverse pairwise. And we want to do it by quote date, put the names of the variables in quotes, and genotype. So you can see here, this shows the ratios of yield for every planting date and genotype combination for every combination of densities. So like, for example, in August 21st planting date in the barcant genotype, the ratio of density 8 to density 1 is about 2. So that would be like this orange bar versus this orange bar is about a ratio of 2. And some of the ratios are bigger than that. A ratio of 1 indicates no difference, right? And let's say, okay, we can see that we thought maybe there was an interaction between genotype and treatment. And we can test that because these are such low yields that we actually have a larger difference between the yields for Marco than we do for barcant by ratio. So we can do interaction contrasts again to test that. So this is how we do the contrast of contrast. We're going to compare the genotype differences with the we're going to compare the genotype differences in the density effects within each date. It starts to get confusing when you have a 3-way interaction because there's so many different contrasts you could do and so many different hypotheses you could test. But this is just an example of one that you could do. So we want an interaction contrast. And what does that show you? So yeah, this shows you that, for example, in the early planting date, if we're comparing density 8 versus density 1, and then we're comparing the effect of that between the two genotypes, the ratio is about 2, although it has a very wide credible interval. So it's like, that means this difference, comparing this difference versus this difference. The difference of the 8 versus 1 effect in barcant on that date versus the 8 versus 1 effect in Marco on that date. It's saying the 8 versus 1 effect in Marco is bigger by a factor of 2, but we're very uncertain about that. We don't have strong evidence one way or the other. That's just one example of something you could do. Yeah, and we still have in just the last couple of minutes, I'll just go over how you might want to present that in a manuscript. If this is your data, how would you write it up in the methods and results? And all this text is in the lesson text, so you don't have to worry about reading it all now. I just wanted to show this here in case anybody anything stood out to anyone they want to ask about. Yeah, basically it's just like last time. We say what kind of model it is and what are the different predictors, what distribution we use, and whether there's any random effects. Yeah, the language is very similar to what we did last time. The same text about about the sampling procedure we did, and that we assess the model fit graphically. And then it says what are the different estimates what are the different predictions we got out of the model, and what are the comparisons that we made, and how do we test them? Yeah, that's what I would put in the methods. And then in the results, we can say, different qualitatively describe the effects and where there was evidence and where there wasn't. Here I didn't put p-values, which would like blow some people's minds, and they would say it's not right because you don't have p-values. But again, if I put if you have all the effect sizes and their uncertainties, that's really all you should need. But again, you could calculate Bayesian analogs to p-values associated with all these things if you wanted to. Yeah, so that's what I would show. The yield ratio between the two density levels was 7.45 with this credible interval. So that's like all you need, right? It's like that's the effect size. That's the difference between the treatments. And we've estimated how big is that effect size and how uncertain we are about the estimate. Why do we need to compare it to a null hypothesis? You really don't, but some people like it. So you could do it if they insist. You can do that. And a figure, I'll just show you an example of how you can make a figure. Again, I did it the same way where I got point estimates of the posteriors and then put some different intervals on it and showed all the different combinations using the tidy Bayes package. So I'll just run that so you can see kind of what you do. But explaining the figure code is kind of out of scope of this lesson because it takes a long time to go through. So yeah, it's kind of like, it should look like the data plot just with model predictions. You want the model predictions to be similar to how the data look, right? So like this looks very similar to the data in terms of the shape of it. It's just that these are now posterior estimates of the means with credible intervals around it instead of the distribution of the data. But honestly, they should be similar. And sometimes you can even plot the raw data next to this if you want to. I kind of like to do that sometimes, although it makes the plot busy. It kind of kills two birds with one stone because it shows the model predictions and it also at the same time shows the model is a pretty good fit to the data because there's the raw data, they follow the model predictions. So it just means these model predictions, while they're just from a model, have a basis in reality because they look like the data. So that's what I would usually do for that. Yeah, so let's see if I have any more slides. Well, that's the end of the material for today. So you may be bewildered by all of that, but it might help you to just go over what we just learned, and maybe that'll help you realize all the cool stuff you've done. Well, we've been through priors. We've explored their influence on inference. We've done a generalized linear model on non-normal response data, binary data, and then we did a generalized linear mixed model for the skewed data. We even had some random effects in there, and we used techniques for a bunch of different R packages. So yeah, let's give ourselves a round of applause. I know you all should be proud of yourselves. You're well on your way. Well, I'll stick around and answer a couple. I see there's a lot of questions here, so I'm gonna spend a few minutes answering them, and then I will. Before I do, I'll say I'm gonna take a break until 1:30 Eastern, 12:30 Central, so like about an hour,
And then I will get back on this meeting, and if anybody, has any questions, that'll be office hours. And then we'll have another class tomorrow, same time, where we'll do lesson 3. So let me quit the screen share here. Oh, wait, people are, could you show how to download the scripts you have written from Posit Cloud? Yes, so if you go in here, okay, so now I've edited this worksheet a lot and I've saved it. All I have to do is go to the File tab over here. And then you can see I've just modified it. I'll select this checkbox of whatever one you want to download and export. In this more, you click on more where the little gear is and hit export, and then hit download and it'll download the file. Yes, so let's see. Do I have an opinion on using JAGs instead of STAN? JAGs is, for those who don't know, is another Bayesian model fitting software that has been around for longer than STAN. Well, I don't want to get into too much detail, but basically JAGs uses Gibbs sampling, which is basically a way that you can use a certain mathematical trick to do some of your sampling faster if the priors follow certain mathematical properties. But STAN doesn't really do that, but it uses a very, very, very powerful algorithm, Monte Carlo sampling algorithm that is just it's awesome. It was made up by quantum physics people in the 80s and works really well. It is, it's called Hamiltonian Monte Carlo. It also, not just STAN uses it. Actually, SAS has a procedure called proc bglim that uses Hamiltonian Monte Carlo. And you can also, other things like Python, MATLAB, all that has Hamiltonian Monte Carlo. It's just a very good algorithm, and the STAN models sample a lot faster. And now that more people have started using STAN, there's all these other downstream packages in R that let you work with the STAN results better that JAGs doesn't really have. So I started using JAGs when I was in grad school, and then when I was sort of halfway through grad school, STAN came out, and then everybody got excited and switched over to STAN and stopped using JAGs. So I kind of mostly learned STAN, but I think JAGs is still good as well. I mean, there's old code out there in the literature that's in JAGs that I've gotten and used for some stuff as well. So hopefully that answers your question. And I see Anna also asks what can you do if the model doesn't converge? So basically there's a couple of different things you can do. Well, first of all, Monte Carlo is guaranteed to converge if you let it run long enough. So you can always add more iterations, but that doesn't help you if it takes a year to converge, right? It's only guaranteed in the long run. So you want it to converge in a reasonable time. So first thing, you could add more iterations. Oftentimes, if you start out with the default priors that are completely flat, the model will not converge. Adding some more priors that will constrain things a little bit helps a lot. That's the main way, is making the priors a little bit tighter. But you can't make them too tight, because then it will, then the data won't be allowed to influence the result, right? So you have to know where to strike that balance, and you kind of learn that with time, I guess. But the priors. And then if all else fails, there's various tweaks you can make to the hyperparameters of the sampling algorithm that can help it converge. But honestly, if you have to do that, you're already lost, because the reason that models don't converge not infrequent is because they're too complicated for the data most of the time. If you have too small data and are trying to fit a really complicated model, it doesn't converge. So you can mess with numerical stuff all day, but really the real problem is that it's not the right model and you're trying to do something that your data don't support. So really it's more yes, you can mess with things, but it should be a red flag anyways, Not always, but it often indicates there's you're trying to do too much with the data that you have. Okay. Thanks for all the questions and the interesting discussion. I'm going to stop the recording here. Thank you again, and I will get off of the Teams and get back onto it in about an hour if anyone has any questions for office hours. Thanks again, everyone. Oh, if asked for p-values, we could estimate them using p-map. Is that correct? You know, yes and no. They are similar to p-values in that they can be seen as a measure of evidence for or against the null hypothesis. They're not exactly the same. You can't just call it, you know, I would not call it a p-value because you would have to specify that it's a similar number. And yeah, how to access the scripts that were used today to try again in R. Well, if you go to the course page, all the information is on there, and yeah, just go to the course page and everything is there. And this, I'm going to keep this workspace on online for as long as I can. I just might, so you can always go in there and get stuff even after this workshop is over. It will not go away immediately, but I just can't guarantee how long. I don't know how much I might run out of space on my Posit account, so I can't guarantee it'll be up there forever. So yes, you should export and save and download the scripts, you know, at the end of tomorrow.